All right, so for us to move into WPA, WPA2, and Enterprise, we're going to start with pre-shared key and then move into some Enterprise modes. And we'll describe a little bit of Enterprise on the way. We need to understand some additional hashing mechanisms to understand how WPA and WPA2 pre-shared key works. We're going to talk about how we can find these networks and then do some assessment methodologies on those keys themselves. And then how do we go and secure WPA, WPA2 pre-shared key? I'm going to give you a little hint that towards the end is that ultimately the best way to secure WPA, WPA2 pre-shared key is not to use it. It's to go to enterprise modes, but we understand that's not always possible. So we'll give you some practical advice if you still do need to retain the use of pre-shared key networks. With WPA, WPA2 pre-shared key, we have the introduction of some new concepts in some hashing algorithms to improve the security of what we had before. WPA was intended to be a temporary solution for devices that did WEP with RC4. The Wi-Fi Alliance and the IEEE said, hey, people, we know WEP is bad, we need to have a replacement, we need to do better, but somebody just bought a wireless adapter yesterday that had WEP, and we don't want to ask them to throw that away. We need to have something that we can firmware update with silicon that was intended to do RC4. Is there something that we can bolt onto the top of the already existing sort of framework to make it better? And the answer was sort of. They were left having to use RC4, but they found some other ways to do some additional components on top of that to improve the security. The WPA with TKIP was intended to be a 5-year Band-Aid lifespan, meaning here's a temporary solution for 5 years. The next 5 years, we're going to mathematically vet and develop the real solution. When hardware has started to go away, we have better hardware that can do more math faster, and we're going to take the time and mathematically vet the algorithms and the methodologies that we've chosen. And I'd say that actually worked out pretty well because we're really now just starting to see some of the issues with new discoverable issues with WPA, WPA2 Enterprise have been coming out now, and it's had a really good run, and I think they did a good job. So with those updated quote overlay solutions to WEP, they're doing some additional hashing for some of the items that we're using for pre-shared keys. And they're doing so by using the HMAC variety of some hashing algorithms. So if we take a hashing algorithm, in this case of MD5 or MD5 sum, and we send some data to it, and I run this command on my system, I'm going to end up with some output. And in this case, the output ending 76B1. And if Zach does the same thing on his system with the same input and the same hashing algorithm, he'll end up with the same output of 76B1. Great, anybody can conduct that if they know what the algorithm was and they know what the input data was. However, with the HMAC MD5 version, we're including some additional entropy to create some additional variance in the output by inclusion of a passphrase to that function. So with HMAC MD5, I'm going to take that same data and I'm going to give it a password of password, and I get a different output. Now, if Zach does the same thing on his system, same data, HMAC MD5, same password, he'll also get the same result. But if Zach doesn't know what the password is, he has to guess. He'll guess maybe P, and then he'll guess PA, and then he'll guess PASS. So it takes a lot more time to be able to recover that same hash if you don't know the password. And we're finding that we're using the HMAC MD5 or an HMAC variety of a hashing algorithm with WPA2, with WPA, WPA2 pre-shared key for some key derivation techniques. And we'll talk about where that password comes from and how it ends up affecting the hashing algorithms and the overall security of these mechanisms. We have that evolution of WPA, WPA and WPA2. WPA introducing TKIP as an overlay to RC4 with WEP. on web-based hardware. And then 5 years later, we had the final ratified standard of WPA2 with AES CCMP, but retaining TKIP for backwards compatibility. And we saw some issues yesterday with some denial of service conditions with TKIP in the way that they chose to do some protections against replay. With both WPA and WPA2, we have the ability to have these in an enterprise environment, which requires a little bit more infrastructure to support our authentication and encryption, as well as a personal version with PSK, so that consumers, direct consumers, our moms and our dads and our brothers and our sisters and our kids could use the same sort of security, but not needing to have all of this extra infrastructure. And back to sort of the same way we were with WEP, with a shared key that potentially folks can remember, and not have to be IT experts to be able to have similar levels of security. I'll tend to say WPA, WPA2 pre-shared key and use WPA, WPA2 at the same time. There are some slight differences between the TKIP and AES portions, and it's largely due to the algorithm RC4 as opposed to AES, and a little bit of different key lengths. The mechanism is the same throughout, so there are very minor differences between WPA and WPA2 from a mechanism perspective. Going into WPA, WPA2 pre-shared key, we have a key that we use to create a key that we use to create a key that is split into a bunch of keys. When we go into WPA, WPA2, what we really need for a starting point to affect our security is the PMK, or the pairwise master key. And in enterprise mode, once we've proven that we are who we say we are, username and password, certificates, depending on our EAP type, PMK is given, pre-calculated and given to us in a secure tunnel. But in a pre-shared key environment, stuff that may be at my house might be a bad example, at my mom's house, at our neighbor's house, my brother and sister's house, I'm the only child, at our family's homes who don't have the infrastructure to support enterprise. They need to be able to drive PMK as that starting point for WPA, WPA2 encryption. So we have to give them another method for them to derive PMK. And we do so with a pre-shared key that we type in that is a secret on both the access point and our access devices. We take that pre-shared key and we do some math, and we use that pre-shared key with the math to derive our pairwise master key, which we do some math with. And then we take that pairwise master key that we've done math to create the pairwise transient key, which is a really long string. And then we split that up into various chunks for a couple of different functions. All right, so how do we get all of these keys? Well, we need the PMK to start. The PMK is 256 bits long, or 64 hex characters. We could have just started there for our consumers and for our users. And do you think my mom would remember a 64 hex character password every time she wanted to join a device to the wireless network? Probably not. I'm really appreciative that we took another shortcut, because while I'm traveling, do you know who tech support is in my house? My wife. My wife's a chemist. She can get 64 hex characters, but the first time the Apple TV drops off the network and she needs to re-enter the password with that remote with one button, she's really happy that we don't have a 64 hex character password. So the intent here with pre-shared key was for the Wi-Fi Alliance to have something easier for consumers to use and have that same level of security. So what we do is we use the pre-shared key to derive our PMK. We do so by taking the pre-shared key that we type in the device, regular keyboard, potentially significantly shorter than 64 characters. The SSID, the name of the network, and the length of the name of that network. And we hash that 4,096 times with HMAC SHA-1. Here's the introduction of our HMAC algorithm, HMAC hashing methodology. So effectively what we're doing here is we're taking this pre-shared key, something that my wife has typed in on the keyboard, and we're HMAC hashing it 4,096 times. The input password to this HMAC function is the SSID. So if I change the SSID, that input password to that hash function changes. The intent here is, one, it takes a really long time to calculate 4,096 iterations of HMAC SHA-1. And there are two components that we need. One, an unknown of the password, and then a sort of known of the SSID. We could potentially brute force this, but we'd have to calculate every password and every SSID possible combination together to create an entire table. And the time memory trade-off there is, it just doesn't work out currently. Okay. This one step is very computationally intensive, and that was intentional so that we wouldn't be able to pre-compute tables, and if we were able to capture all of the information, it would still take a long time to potentially brute force. We take our pre-shared key to derive our pairwise master key. We then take our pairwise master key to create our pairwise temporal key, which we split up, with some additional information with the network. We take the MAC address of the client and the MAC address of the access point, and two nonces, two unique values exchanged in the clear, in the air, one for the client, the station, and one for the access point. So lots of additional entropy. We obtain the MAC addresses, we obtain those unique values, the nonces. We send those to a pseudo-randomization function to derive this really long key. And we have the ability to, as we're progressing a number of packets, to change those unique numbers, those unique nonces, to recalculate keys so that we now have a fresh set of key material. Okay. So we use that PMK with the two MAC addresses and the two unique numbers exchanged in the air and the clear, and we'll show this a little bit more visually, to generate our PTK using a pseudo-randomization function. And we now get this long string that we split into a bunch of different keys. So depending on whether we're using TKIP or AES, the key length will be different, but we still have some standard chunks out of those lengths in which we split those out to various keys for doing message integrity checks and actual encryption of the data. Of that PTK that we've generated from our pre-shared key to our pairwise master key and now to our PTK, a pairwise transient key, we split those into an HMAC message integrity check key, an EAP over LAN key for key encryption key, the temporal encryption key, and two TKIP Michael keys. The TKIP Michael keys are the ones that are used to derive that checksum value, so that when we change that queue number, the message integrity check is invalid because we didn't have the right password to update that, even though we updated the content. So denial of service-based attacks there. So key, math to beget key, math to beget key, to split a really long string into a whole bunch of keys. Pretty complex operation. If we think about some of the things that we need here going into pre-shared key, we need a pre-shared key. The user types that in. It's a secret on both devices. We need the SSID. The user, it is typically in the air as a beacon frame, or we put that on the devices when it's hidden and it's defined on those devices. We can also observe that in the air on hidden networks. We saw that on day one. We then move into PMK to derive PTK, and we need MAC addresses. Now, MAC addresses are always unencrypted. We've seen that with doing some sniffing for both the access point and the client, so we can get those. We now also need the nonces, those unique numbers. And those are transmitted in the air, in the clear, at time of a device joining. So there's lots of moving parts. There's lots of moving parts that are in the clear and that we can deduce by doing observation of traffic. So in order to get those nonces, both sides have to have both sets of nonces. And I calculate mine and I have mine, but I need the access points. And the access point needs mine, so we have to transfer those in the air. And we have no keys to be able to create an encrypted tunnel, so they are done in the clear. We do this at time of join of the network per session, so that we have per session unique keys per device, because they're based on device uniqueness, those nonces, for the device and their MAC addresses. At the time for that session, you disconnect, you reconnect, you go through this new exchange of nonces. And this is what's known as the four-way handshake for WPA, WPA2. So I go to join the wireless network. Access point says, hey, we need some information to send back and forth so we can calculate PTK. You need my nonce, you need my authenticator nonce. Here it is, and let's create new PTK. The client then receives the authenticator nonce, calculates its supplicant nonce, its client nonce, says, hey, I have everything I need now to calculate PTK. Calculate PTK. Oh, wait, the access point says, still needs my supplicant nonce so it can calculate PTK too. So takes that nonce, creates a message integrity check of that frame using the PTK it just calculated, sends that to the access point. Access point says, hey, I've got everything I need now. I've got my nonce, I've got the client's nonce. Calculate those, grab PTK, and then I can confirm based on the message that I just received that, yeah, the PTK that I just calculated will match the fact that these are the right ones. Nothing has changed in transit through these message integrity check keys. And so the message integrity check of frame 2. The authenticator, the access point, then sends a response back, kind of like an acknowledgement of, yeah, I've received your nonces, I've calculated PTK, the message you sent to me checked out. Here's a message to you to make sure I had the right inputs too, so you can verify that, hey, we both have the correct output for all of these functions. Client then says, yeah, absolutely, mine decoded properly. We have the right pre-shared key. We have the right SSID. We calculated everything based on our MAC addresses and nonces properly. Here's a confirmation with another message integrity check of our frame, and now we're ready to do data. So this four-way handshake of exchanging unique numbers, the nonces, performing the math, and then confirming that the math was correct. Cool. So if we think about this process, we've recovered a bunch of stuff out of the air. Looking at this, this is message 2 of 4 for the four-way handshake, in which we're exchanging some really long unique numbers per device for those nonces as input to PTK derivation. So if we think about what step 2 was, this is the client responding back to the access point with its nonce. This first one, message 1, was the access point giving its nonce to the client. So how do I identify that WPA, WPA2 pre-shared key is in use in the environment? Well, we start taking a look at some of the beacon frames. Beacon frame headers will oftentimes say, yeah, we have the privacy bit set, which could also be WEP. But then we dig into some of the other information elements in those beacon frames to determine whether WEP header exists and those unique IVs in the data, or looking further into the beacon frame to see if there's additional descriptors in those beacon frames about which types of encryption we should use. And by doing so, by looking at those beacon frames when the privacy bit is potentially set, we can determine the cipher suites and the authorization, the authentication key management for WPA, WPA2, pre-shared key, and enterprise. We can look at those beacon frames and looking for specific management tag number information elements in those beacon frames by specific numbers. specifically management tag number 48 for WPA2, if I remember correctly, and 221 for WPA with TKIP. 2 weeks ago when I was working on an assessment, because I could have sworn there was a TKIP network there, because I wanted to make sure that we advise them don't use TKIP because of denial of service, and I know you're hosting a bunch of stuff on APs. And I went and searched. I had to go back and open up my own slides so I could remember the numbers. And sure enough, it was 221. And sure enough, 221 in a Cisco environment is also used for additional informational elements specifically related to Cisco type of stuff. So some of the beacon frames were just, they had like 5 and 6 information elements of 221. But they were identified as being, hey, this is the Cisco one and this is the Cisco one. But the one that I was really looking for was the Microsoft one. All right, so taking a look at some of these beacon advertisements. This is the beacon for the Harkonnen network. And the robust security network information for one of the information elements there is tag number 48 from Microsoft. And looking at that, the cipher suites are AES CCMP, and the auth key management is pre-shared key. So we have a WPA2 pre-shared key network in this case. Looking at TKIP, the vendor-specific 221, and some of the updated ones do say that the vendor-specific is Microsoft. Okay. Our multicast cipher suite and our unicast cipher suite are both TKIP, and our auth key management suite says WPA. WPA is indicative in TKIP of pre-shared key. Otherwise, it would say enterprise. All right, so we can discover that pre-shared key is in use by 48221 and looking at the specific cipher suites and auth key management suites. Thinking about the inputs into the pre-shared key function, we have a whole bunch of stuff in the air. We have MAC addresses, we have SSIDs, either in clear text or recoverable. We have nonces in the air. We have message integrity check confirmations in the air. But we're missing one component that's always a secret and never transmitted, and that's the pre-shared key. And that's what the users type in on the device. Okay. The IEEE specified for these pre-shared key that they should be between 8 and 63 characters. However, through their discussion and looking towards the future, in 2007, the IEEE said effectively that any passphrase that you pick that is under 20 characters for a pre-shared key is going to be considered weak because brute force methods will recover those within a reasonable time frame. However, the specification, they threw up their objections. You shouldn't pick a password less than 20 characters. However, the final specification says that you can have a password as little as 8. And this really became the Wi-Fi Alliance saying, if you have users put a 20-character password in 2007, they'll never adopt this. You need to make this easy for users to use. Okay. So what do people do? They do the absolute minimum. They put in an 8-character password. I'll tell you right now, pre-shared key for my wireless network at home is an 8-character password. Why? Because my wife has to type it in on a 1-button remote. Okay? So it's easy for my wife to use. Some other networks in my home that they aren't on have significantly longer passwords in the order of 30 plus characters. We often issue this as a finding in some of our reports if they have pre-shared key networks and the passphrase is under 20 characters, because this has been known to potentially be weak since 2007, and it can be easy to crack passwords under 20 characters. We had a finding with one of our recent customers before we even started the engagement. They were asking us to evaluate the wireless configuration on a client device that they were offering for sale, and it would come pre-configured in some varieties. So we set up a wireless network and they configured it for us so that we could be testing the device as it was for sale for the consumer. And we gave them the network name, and we gave them the password, and the password was 24 characters long. And they came back and said, yeah, you're going to have to pick a new password. Why do we need to pick a new password? Oh, because the device doesn't support a password over 20 characters. Well, there's a finding right now. We haven't even started the engagement. You haven't even shipped us devices. And if you pick a password less than 20 characters, we can potentially crack it. Oh. Yeah, it turns out the way they were storing the passwords, because they'd listened to our device in the past, they were storing the passwords encrypted on the device itself. Like, not in plain text, that's good. But the algorithm that they chose, the field length that they picked, the longer the password was, the longer the output encryption was. And that they couldn't support anything longer than a 20-character password because they just didn't have the room to store it. I'm like, well, yeah, catch 22, right? Damned if you do, damned if you don't. Okay, so we still gave them the advice that they need to have longer than 20-character password. Thinking about that, Mr. Moskowitz in 2003 wrote a paper about the pre-shared key selection weakness and selection bias, in that if we've given users the ability to pick an 8-character password, even though we know everything under 20 characters is going to be weak, what do users do? The absolute bare minimum. So he thought about that and said, yeah, pre-shared keys are weak because users will pick 8-character password. So let's go now test all 8-character passwords for our wireless network once we know the SSID. Josh developed a tool called CowPatty for doing offline attacks against WPA pre-shared keys by using a dictionary to implement what Mr. Moskowitz had illustrated in his paper from 2003. It's since been made public, and it's the code has been reused in a bunch of other tools as well. Well, effectively, what CowPatty does, and the basis for many of our other tools that are doing password guessing for WPA, WPA2 pre-shared key, is we catch the 4-way handshake, the exchange of nonces, we give it the SSID, it calculates the length, we capture the MAC addresses from those 4-way handshakes. We have everything we need in the air, those nonces and the message integrity checks. And now we go to a dictionary and we use that dictionary to try to guess the password offline using packet captures not active against the network. It is time consuming because we have, for each one of those password guesses, we have to calculate 4,096 iterations of HMAC SHA-1. All right, so how does it work? CowPatty takes some input from a PCAP file, the PCAP formatted file containing a 4-way handshake. It collects the 2 addresses, the 2 MAC addresses, the authenticator address and the supplicant address, the client address, the 2 nonces exchanged in the 4-way handshake, and the observed message integrity check of the last confirmation in frame 4. It goes to our dictionary of words, reads a word, calculates the PMK using that word in combination with the SSID, which is computationally expensive, 4,096 iterations of HMAC SHA-1, to derive PTK, takes PTK, calculates PTK with our addresses and our nonces, splits those off into our keys, calculates the last message, recalculates the last message with our key to see if those message integrity check at step 4 matches. If they do not, the calculated message integrity check versus the observed one from the packet capture, if they do not match, that means we had the wrong pre-shared key. So we go back to the dictionary and we start all over again with our 4,096 iterations of HMAC SHA-1 and try it again. If the calculated matches the observed, we guessed the right password from our dictionary and we've recovered the pre-shared key. This works great with dictionary-based words or really large dictionaries. This is a CPU-based operation, so it is potentially quite slow. So looking at this example of CowPatty using a 4-way packet capture, a dictionary, the -F pass list, and the SSID of our ping pong wireless LAN, or our GNIP-GNOP wireless LAN, CowPatty on some modest systems, in this case, 73 passphrases a second. That's not terribly fast, but it is the methodology for how many of the other tools are doing so, whether it be brute force, guessing all the possible values, or more robust dictionaries. AirCrackNG also will do the same methodology with a word list. And Josh actually has authorship credit on AirCrackNG. And he doesn't understand why, because he didn't write a single piece of code for it. What happened was that they gave him credit where credit was due, because they reused his cow patty code within AirCrackNG. So he now had authorship credit. Right. Arguably, AirCrackNG does it a little bit faster. They did make some improvements. And in this case, 91 keys per second out of the dictionary. Again, still not terribly fast. We can make this faster. A RenderMan, Brad Haynes, Canada's finest wireless hacker and a good friend of mine, said to Josh, your cow patty thing is amazing, but let's use it to make rainbow tables so we can just pre-calculate all of these things and be done with it. And Josh said, Render, that's a really great idea, but the problem is that we have that HMAC algorithm for the SSID. We need to calculate every password for every possible SSID. Oh, well, yeah, that's a problem. Well, let's just do the top 1,000. RenderMan, where are we going to get the list of top 1,000 SSIDs? Well, that stats page from Wiggle, similar types of things. They also know the top 1,000 SSIDs. So RenderMan created a dictionary of like 16.8 million words and took the top 1,000 SSIDs and said, great, Josh, we've got the input. How do we make it happen? So Josh split off a portion of his code from cow patty, the PMK generation, the 4,096 iterations of HMAC SHA-1, and then used the top 1,000 SSIDs and the pre-shared keys from the dictionary to be able to calculate a lookup table for those, for all 1,000. Josh wrote the code, gave it to RenderMan. RenderMan was going to do a talk at ShmooCon about rainbow tables for pre-shared key and so forth and so on. And it was going to be this really big deal. And it was a really big deal. Everybody's really excited to see it. And RenderMan spent 3.5 months on his desktop PC in his apartment generating all of these tables using Josh's code. And it got done. And RenderMan set up an access point with one of the top 1,000 SSIDs with a password near the top of the dictionary, captured the four-way handshake, and used cow patty with the dictionary, with the rainbow tables to crack it. And it didn't work. So he said, maybe I typed something wrong, did a different password in the dictionary. Didn't work. So we set up another SSID of the top 1,000, different password, tried it, didn't work. So needless to say, there was a very angry phone call from RenderMan to Josh, and RenderMan says, Josh, your tool is broken, it sucks. I just wasted 3.5 months of my life calculating these tables, and because the tables don't work, I now have to resign my talk from ShmooCon because I don't have any work product. Thanks for setting me up to fail. And Josh's comment was, well, wait a minute. I did the same thing you did, but I just calculated 1 or 2 and it worked just fine. So what's going on? Let's troubleshoot this. Well, it turns out GenPMK is a Linux tool, and RenderMan's a Windows guy. At least he was at the time. So he created his dictionary on Windows, and he copied it to Linux. Extra carriage return line feed at the end of every password, which Linux interpreted as being a part of the actual password. So there was like either a carriage return or a line feed at the end of those passwords that he spent 3.5 months calculating. So yeah, his dictionaries were garbage, and the tool did exactly as it was told to do. So he's like, now what? So RenderMan called up a buddy of his, Hikari, David Hulton. And David Hulton was very heavily involved in a company called Pico Computing at the time. And Pico Computing sold field programmable gate arrays, FPGAs, processors that can be programmed to specifically do types of math very fast. And Render described the problem to him as, oh yeah, RenderMan, totally fine. Next time we're at ShmooCon, buy me a beer. I actually just had this shipment of E16 FPGAs come in. And they need some burn-in tests. And we can totally do HMAC SHA-1 on these. Send me your stuff. I'll download them. And we'll burn-in test these E16 FPGAs. 4 days later, there was a hard drive with these tables shipped back to RenderMan like a week before ShmooCon. So Hikari was able to compute using like $750,000 with FPGAs, the same in 4 days what it took RenderMan 3.5 months to do. So, success. RenderMan did the talk. It was a great success. They put the tables up on BitTorrent. RenderMan said, who wants the very first copy from Hikari? And he's got it on a 3.5-inch hard drive. And everybody's in the, we don't want to have to download that from BitTorrent. Yeah, I want it. And RenderMan takes his hard drive and goes, whoosh. He just chucks it into the crowd. It's like throwing a brick at a crowd, and no one's wearing face shields. Yeah. Fortunately, no one was injured. But we now have some rainbow tables for this type of stuff. And absolutely, we can use this same methodology with a really good dictionary. And if we know what the SSIDs are of some environments that we want to test, we can pre-calculate these before we even get on site. Do all of the hard math up front, so that when we get there, capture the four-way handshake, we can go through it in potentially a couple seconds. It may not always be successful because it really is reliant on the content of our dictionary. We can also do these same sort of things with Hashcat and some GPU-based acceleration. You guys are going to do this as part of some of your lab. You're going to use CPU-based. It should take 5 to 10 minutes to complete. And we want to make sure that we're very smart about this because we're actually going to do brute force operation. We're going to use some powers of deduction to look at some passwords and how we see them constructed for other devices so that we can apply those same sort of rules to our devices. And of course, the more GPUs we have, the faster this operation can be. And every time we update this slide, the new devices come out with even faster hash rates. So it's kind of like fighting a battle here. In order for us to do pre-shared key cracking with Hashcat, we need to have the four-way handshake, and we need to convert that four-way handshake into a file format in which Hashcat can use. There are utilities out there to be able to perform that, such as cap to HCCCapX. And then we can do all of the standard Hashcat function word list with rules and true brute force for all of these using the power of GPUs. All right, so in this case, this is similar to what you're going to do during lab. You're going to investigate a set of passphrases, and you're going to see some commonalities. So that the passphrase that you'll be looking at during lab is like 22 characters long. But you really only need to brute force 6 characters, because based on what you're seeing, you can deduce that there's a static phrase. You can deduce that this portion is based on the MAC address. And you can deduce that the random stuff that you have to crack is also then separated by a dash. So by looking at a sample password, you don't have to crack 22 characters. You can deduce a good portion of it, and then only end up having to do like 6 or 8 characters. And then even then, potentially even reduced character sets. So looking at this particular one for these reduced character sets, this is an 8-character password for this Verizon MiFi. I love going into the AT&T store and the Verizon store and looking at the default passwords on the back of the devices so I can see how they're constructed. And looking at this particular one, we see these character sets of, letters and numbers. Great, so now I have all of the letters and numbers to brute force for an 8-character password. But do I really? Is there a capital letter in there? No. Is there a letter over F in there? No. It's a good chance that the letters are actually hex characters. So 0 through 9, A through F, all lowercase. That significantly reduces my character space in which I have to test for. And yes, absolutely, we can use Hashcat to go through that a heck of a lot faster with our reduced character space, have it take just a couple of minutes as opposed to having to test all of those. I'll go for a shorter run and be more aggressive about my character selection first than go for the long one and have it potentially take weeks, days, or months. Okay. So some methodologies here, thinking about how we can start being smart about those brute forcing. So we can convert to our HCC cap X. We attempt to do brute force using 8 lowercase letters, the L signifying the lowercase letter. Will that work? No, because there's numbers. Okay. We preface it with a static string of ASDF and 4 lowercase letters. Will that work? No, because a static string is not ASDF, and we have numbers in there. Okay. But we deduce that maybe there's some better character sets we can use. Recent versions of Hashcat 5.0 and above actually have a hex character set defined. So 0 through 9, A through F. And I think it's $H. So instead of having to create our own custom character set for one referencing our character set, we can use the built-in ones now too. Okay. I believe that the version that you guys are still using does require us to create our own character sets. But even if we don't, it's still valuable for you to learn the exercise about creating custom character sets, even because it may be something outside of those. Looking at this command is very similar, if not the exact command that you will use during lab. So some great reference to go back to, because it's very easy for us to potentially have too many, and then it will take weeks, months, and then, well, that lab will really run on long. But this is very similar to the format that we'd be looking for here. And looking at the time here, on my older Mac in a virtual machine, it took just over 6 minutes to crack the password here, because we were really only looking for 6 numbers based on how we were able to deduce how the password was constructed. Instead of spending lots of money on GPUs, we can go to Amazon and use their GPUs as well. And on this one, as soon as we put a price for the hourly rate for their big GPU boxes, the price changes, and which region you're using it in and which time of year based on cooling costs. So type is variable, but it's a reasonable cost for across the board as an average. Okay. Some things to think about. Just be careful using these instances, because if they are running and you're not cracking stuff, you're still incurring cost for the use of these, and can get quite expensive based on the number of GPUs that you're using. The big one is if you go and do the crack and you let it run for a couple of hours and it cracks and then it's still up running, you're still incurring costs. So get those things shut down as soon as you're done. I had a friend who was quite some time ago was looking to use Amazon's GPUs for doing Bitcoin mining, when Bitcoin price was significantly lower. So he was also made a mistake in the type of instance he used. Instead of using a spot instance, he used a dedicated instance, which is significantly more expensive. And he went and fired off his Bitcoin mining stuff with their GPUs. And at the end of the month, he got his credit card bill, and he had a $3,000 bill from Amazon. And he kind of freaked out. He didn't realize that he'd done the dedicated as opposed to the spot instance. So he called up Amazon, and they said, yes, Mr. Finch, we understand these types of things happen all the time. We're going to give you one get out of jail free card. We will, in fact, revise the billing as if you had used a spot instance, as long as you shut those down within the next hour or so. And he did. And he recovered his wallet, and he hadn't earned $3,000 in Bitcoins at the time. I think maybe if he'd held on to them, we might have broken even. But at the time, he also hadn't made the $300 in Bitcoins that actually cost him. So it was a lose-lose situation all around. So just be very careful about your instance management doing these types of things. Ask me how I know this, okay? Or ask my friends how they know this. Pre-shared keys are hard. Like, my wife needs to remember an 8-character password. Wi-Fi Alliance said, well, we want everybody to adopt this. Yeah, 20 characters, yeah. All right, we understand we want 20 characters or better, but this is also really hard. How can we make it easier for consumers to better protect themselves? So they developed a methodology for pre-shared key exchange over the air in a protected tunnel, requiring input from the user with a PIN to be able to affect that exchange, called WPS, or Wi-Fi Protected Setup. Let's print a PIN right on the bottom of our access point, so when the user wants to define a new device on the network, they can just go to their access point, type in this 8-number PIN, and we'll give them a 20-character or more pre-shared key automatically to their device. What could possibly go wrong? Okay. Let's make it easy for the user to make this happen. Typically, we are seeing this with the PIN method. Once we try to connect with a WPS-enabled network, it asks for a PIN. We type that 8-digit PIN in, and it creates some Diffie-Hellman keys for us to be able to exchange information in the air securely, and then sends us the pre-shared key, potentially 20 characters longer in the air. Super easy for the user to use. We're typically finding, we are only finding WPS in consumer-grade hardware. WPS has not been implemented in enterprise-grade hardware. However, we do discuss this here specifically because what happens when your staff takes their laptop home into their environment? We now potentially have evil attacker looking to interact with that enterprise device on a lower security network, one that is featuring pre-shared key with feature sets that may be vulnerable, so they can directly interact with that machine on a lower security network. All right, so let's talk about the WPS PIN authentication mechanism. The Wi-Fi Alliance kept it a secret. If you wanted to understand what the security mechanisms were, you had to license the technology from the Wi-Fi Alliance. It wasn't terribly expensive to license it. There's a minor barrier to entry. However, Microsoft leaked a lot of the, quote, intellectual property outside of their non-disclosure agreement, maybe arguably incorrectly, about how to implement WPS in a Windows environment through their Developer Connect Now program. And what we learned from that was the way in which WPS processes the PIN when it is received. What happens with that PIN is that it takes the PIN and it splits it into two 4-digit chunks and evaluates both of those chunks independently. And then we'll tell you which part you got wrong. How convenient. So what this really means at step 1 is that if we were going with an 8-digit PIN, all numbers, for our WPS PIN, we were talking 100 million possible guesses that we would need to make to brute force it. With this one step of conducting it into two 4-digit sections that are processed independently, and you'll be told which one, we now move to 10,000 guesses to 10,000 guesses. 10 to the 4th to 10 to the 4th. We also learn that the second half of the PIN is not really a 4-digit PIN, it's really a 3-digit PIN and a checksum. So the PIN is really only 7 digits, 4 and 3 processed independently. So we have 10 to the 4th plus 10 to the 3, or 11,000 possible guesses needed to brute force WPS pins. We went from 100 million to 11,000 possible guesses. Hooray for the Wi-Fi Alliance. I'm not a huge fan. They have so much opportunity to do great things, and I think they continue to screw it up. We'll see some more of this with WPA3. All right, so Wi-Fi Alliance with WPS, maybe they didn't think about what the actual mechanism was and what this would mean. Sure, it's easier for the user and we can have them distribute stronger passwords, but the mechanism in which they chose to do that is actually pretty weak and actually significantly weakens the security of what they were intending. So taking a look at this, we have the WPS indications in a beacon, and in this case we have Wi-Fi protected setup state as configured, meaning it is a feature set of this access point. So WPS is enabled on this access point as part of the beacon frames. Hey, my network, we support WPS. Okay. Make sure you use an updated version of Wireshark so that they can properly analyze some of this data. How can we attack this? Absolutely, we have some tools. One of them being Reaver from Tactical Network Solutions, a tool for us to be able to perform online-based attacks. We need to have the network present so that we can guess pins, create Diffie-Hellman keys, and then eventually get the password sent to us. It randomizes the pins, tracks which ones have been used, retains session state so that we can stop the tool, and then restart it later for that same network and pick up where it left off. One of the ways in which they've chosen to start doing some protection against WPS is that if you have too many incorrect guesses, they'll institute a hold-off timer. Hey, you can't guess for another couple of seconds. And sometimes it will even shut it down altogether. So do it in small chunks. And it's not terribly fast, but we don't have that many guesses to actually do. So Reaver in monitor mode for our interface, attacking a specific wireless network based on our BSSID, our MAC address. And in this case, we're being very verbose to see some of the output. And it goes through and it finds the network and switches to the appropriate channel, attempts to associate to the network, in this case the fancy Flamingo network, and then guesses pins. And then makes some decisions based on those pins, and we've got the first part right down about here, 6843, 6843, 5516, 5526. We've been told that the first half was right, so now we're just guessing the remaining part. And looking at both of these, the 6 as a checksum was correct. So now we're only guessing 3. Okay. Turns out 684-35226 was the the pin for WPS. It took us a little over 4.5 hours to conduct the attack. Take that pin with Reaver and it automatically asks the network, hey, can I have the pre-shared key now? Here's my Diffie-Hellman keys. And the access point happily returns the password, in this case, for the fancy Flamingo network, of a very complex password that you won't guess with cow patty. Guess what's in my dictionaries? Okay. Also with correct battery horse staple. Okay. Put those in your dictionaries too, because you'd be surprised even though you're told not to use those, people use them. So now what's the problem? Oh my gosh, you got my pre-shared key. I'll go change my pre-shared key. WPS to get those on the new devices. I still have your WPS pin. I'll happily go get the key too. We do need a Reaver to be in an active mode. However, we can also use the WPS pixie dust attack as a passive offline attack. We can gather some data about the network and attempt to be able to do similar types of operations with some specific Reaver forks to gather some key-based material and perform offline attacks for this. So we're not interacting with the network. Turns out some of the implementations of WPS in their random number selection for the math and the Diffie-Hellman keys aren't really all that random. So some of the WPS implementations are faulty. So not all of them are faulty, but some of them are, a good number of them are. And that we can deduce the actual pins in an offline manner by exploiting some of those implementation flaws. And we saw in the traditional Reaver approach, the online attack, it took 4.5 hours. Could take longer. We got lucky towards the middle of the pack for those pins. With the pixie dust attack and exploiting those particular networks that have the not so random number generation, offline, this can take potentially seconds, not hours to conduct. Okay, so even faster. All right, so Pixie WPS is the tool after gathering some data with an updated version of Reaver to actually display us some of that, the numbers that we need to conduct the math. Okay. It's all there in the Reaver tool. It's just not easily spit out to us, but the updated ones do. So why do we talk about WPS if it's not in enterprise gear? Well, we often find that WPS is potentially enabled on consumer grade gear. And for a long time it was on by default. I'm starting to see it is becoming less on by default, but I still know of a number of folks that use it just because it is so easy to use. And from the enterprise perspective, if your users of your enterprise gear who take them home to write emails and reports and do work at home or work from home may have them in an environment that is of a lower security settings, and the attackers would go where the low-hanging fruit are. So this is incredibly low-hanging fruit for us to gain access to a network to potentially directly interact with your enterprise devices there. Okay. So just go change your PIN, right? Well, for many years, the manufacturers did not allow for the PIN to be changed. It was fixed in hardware and was printed on the bottom of your device on a sticker. I've started to see some of the manufacturers allow you to update the PIN, but then again, it's a PIN that is still vulnerable to some attack, whether it be with Reaver or WPS Pixie Dust. So disable WPS all over the place. The other one that we've got is some other low-hanging fruit. Instead of gathering stuff from the air, whether it be WPS or the four-way handshake, we store the PMK or the pre-shared key on the devices as we're using them in the environment, so that every time we go to connect to a wireless network, we don't have to type that password in. It's easy for us to just have that stuff stored. So go steal a device in the environment and get access, physical access to the device. And once you have physical access, you can now recover the key. Now the challenge becomes, this is back to a little bit of a WEP problem with the WEP shared key. How do you rotate the pre-shared key in an environment when you suspect it may have been compromised? I ran into this situation a while back in that some folks were recommended that they rotate some keys. They couldn't figure out the best way to do it, so they just didn't. And it potentially could have come back to bite them later. We have a couple of ways if we have physical access to a device to gain access to the keys. One of them is a tool from Nersoft, Wireless Key View. GUI application, works on every version of Windows that I've tested it on, including the most modern versions of Windows 10. We'll go and grab the pre-shared keys from the configuration files and use the appropriate keys on the system to decrypt them. Okay. We can also do it from the command line output, and we can also do similar type of operations with PowerShell as well if we don't want to use the GUI tool. Once we have a pre-shared key, we can use Wireshark to decrypt that, but again, Wireshark won't spit out the decrypted contents into a new file for us. So much like we did with WEP, we use AirDecap NG with the SSID and the pre-shared key to decrypt our packet captures and write it outbound to a new file, so we can then use that decrypted stuff with other tools. What about this whole crack thing? It's the key reinstallation attack against WPA networks. And this is really using some math that goes way over my head. The irony here is that it was found by a gentleman by the first name of Matthew, which I think is also appropriate. Apparently he's really good at math. Okay. Matthew Van Oof found that, discovered the key reinstallation attack. And key reinstallation attack is effective against networks that have WPA, WPA2, and or fast roaming. So 802.11i or 802.11r. And many networks do feature fast roaming, whether or not you know it. Okay. Effectively, what Matthew found was that if you are asked to rekey by exchanging new nonces, after your 65,000 packets are up and as part of the process, if you replay your old portions of your four-way handshake the devices, the access points will happily accept that replay of the old one and will use the old keys instead. They'll go back to memory and then reuse those old keys and push those back to the driver. So in fact, we never do key rotation. And when we're never doing key rotation, we have the opportunity to have the same keys using more data. And we're now back to potentially password deduction attacks because the key has been used for the same data over long periods of time. This is the similar type of thing as if we can force the reuse of the key and we know plain text, we can now deduce the key. Remember, very similar type of techniques for the way that the Allied forces were able to break the Enigma with the Bomba, because every one of the messages from the Germans had the same phrase at the beginning of the message. Different key, same static phrases. And also weather reports were amazing for this stuff because they could observe the weather and they could tell sunny, cloudy. So they were able to do other plain text and was some absolute great shortcuts for being able to do key deduction to effectively break the Enigma. Similar types of things here is that once we have the same key in use and we can now deduce plain text, we can also recover those keys. So it also affects 802.1x key distribution for TKIP, CCMP, or some of the new GCMP with wireless gigabit or WiGig. So not only does it affect pre-shared key networks, it also affects enterprise networks because we're effectively forcing the devices to reuse keys. All right, so what does this do? Crack works by capturing and replaying step 3 of the four-way handshake. We observe a device redoing its four-way handshake to exchange nonces. We interject the previous step 3 that we observed in the last step, okay? And then do denial of service for step 4 so that the client never receives back step 4. I'm sorry, the access point never receives step 4. So we're telling the client, hey, reuse that same key we did last time. Hey, reuse that same key we did last time. Once the client accepts that replay of step 3, it goes back to memory and reinstalls the key from memory back to the driver so that we are now using that old key to actually do encryption of traffic. So if we continue to do that with that same key, we have the ability to, with known plain text, reveal the PMK through key deduction and so forth. Once we have PMK, we now have everything we need to decrypt and encrypt traffic on those networks. We had some issues with some devices that were really considered to be more secure on this, in that OpenBSD and Android made some decisions about how they were going to store those keys before they were pushed to the driver. Windows, Mac OS, the key stayed in memory in a specific section of memory. We grabbed 3. The drivers and the stack would go, oh, hey, yeah, the key is in memory here. Go grab the key and push it back to the driver for encrypting the data. With Android and OpenBSD, they made a conscious decision of, hey, what happens if someone steals our devices and captures memory? They can pull that key out of memory. We don't want that. So we're going to take that key that we used once, that we pushed to the driver, and now we're going to wipe the key with all zeros. So now when we replay step 3 with crack, it goes, oh, hey, the key is over here in memory that we've just wiped with zeros. So now the key is zeros, and we push a key of zeros to the driver for encryption. We didn't even need to do any reverse key mapping because we knew the key was all zeros. Yeah, they made a good decision to remove those keys from memory until this happened. So that became really terrifying. It's all known values. Once we know this key once we know the PMK through the crack attack, we have everything we need to encrypt and decrypt traffic to legitimate access points and create our own access point for clients to join, which we can then become man in the middle. We create our own with that PMK on a different channel, deauth the legitimate device. It finds us on the new channel, and we didn't even need to crack pre-shared keys. This is terrifying because not only does it deal with the pre-shared key stuff, but also all of our enterprise-based methodologies and our EAP types where certificates and usernames, passwords, and potentially two-factor authentication come into play. This defeats all of those protections as well. Okay. So in the demos from Matthew Vanoff, his video shows the ability for us to recover the PMK, denial service a device, make it join our evil one with the PMK we recovered. We can encrypt traffic. The client device has no idea anything has changed because everything is encrypted and decrypted properly. They're doing HTTPS, SSL over that connection that we're now man in the middle of, and then Matthew uses SSL strip to remove all of that data too. So even though we've tended to rely on higher level protocols to encrypt some of that, there are tools to get away around some of that. Okay? So getting rid of some of the protections, rely on higher layer protocols even though you think you're doing a secure wireless network. The big thing to note is that these attacks require physical proximity to the client device and the network in which they are connected to do the key reinstallation attack. You can't have a device show up at Starbucks not connected to the network and launch the crack attack. It needs to be in an active state so that you can obtain the step 3 and replay it actively and then get it lured to you. So not something that we're just going to show up at Starbucks and start attacking folks. It needs to be in the presence of the initial and or active connections to start. Why do we care? Well, there's largely academic pursuits of the crack attack. Matthew has deployed some test tools to see if you're vulnerable, but there are no known attacks publicly available or attack suites. But I can see that this is sort of the next attack that is going to get really well developed, specifically because it affects WPA2, pre-shared key, and enterprise. And we've already seen folks starting to try to recreate Matthew's work based on his demonstrations and his papers, but they're not quite there yet. So coming soon, and has the ability for us to have a potentially very damaging attack against what we would consider some of the best wireless security available now. WPA3 is potentially broken, and or if not, have some time before it's fully broken with a release of attack tools. What about WPA3, the new subset of wireless security introduced by the Wi-Fi Alliance, who's a certification body? They said, yeah, WPA2 is broken. We've got the next thing since sliced bread. Here's WPA3. As we saw with the Wiggle outputs, there were 3 out of 580 something million access points that featured WPA3. Maybe the tools didn't know how to acknowledge that it was WPA3 yet. So really low on the implementation. But looking at the feature set of WPA3, the Wi-Fi Alliance had this really great thing that I think they did. They changed the way we handle the pre-shared key and pre-shared network, pre-shared key networks by using simultaneous authentication of equals plus the 4-way handshake by utilizing perfect forward secrecy. So some additional math in and above the 4-way handshake to reduce the ability for us to do offline pre-shared key cracking. That's great. They've done away with WPS and used the device provisioning protocol, another protocol that they developed to replace WPS. They didn't have a pretty good success run with WPS, did they? But at least they acknowledged that it was weak and tried to do something better. They give us the opportunity on a, quote, open wireless network, the ability for us to anonymously create some encryption keys using opportunistic wireless encryption, or OWE, so we can encrypt data on an unauthenticated wireless network. That's cool. Also implemented the ability for us to move away from TKIP and AES CCMP using 256-bit AES GCM, elliptic curve cryptography with 384-bit curves, SHA-384, so forth and so on. this is amazing. Like, this really raises the bar for now how we're going to have to, interact with wireless networks to defeat the encryption and defeat the authentication, and maybe now no more open wireless networks with unencrypted traffic. But the Wi-Fi Alliance had this great thing. And because they're a certification body, they're the ones that get to put the little stamp on your devices to say, yeah, you're certified for WPA2. Their WPA3 certification stamp only requires that you perform simultaneous authentication of equals to obtain the certification. Everything else is optional. They had a huge opportunity to blow our minds and to do amazing things for wireless security up and above WPA2. And they chose to do the absolute bare minimum. I'm not particularly fond of the Wi-Fi Alliance, can you tell? That said, you can, as an implementer, implement more, but the base minimum to get your stamp is SAE. And even if you do implement more of these things, you're now going to run into problems where this client doesn't support elliptic curve cryptography for our encryption types. This client does, but the access point doesn't, so now we can't do the better things. All right, how do we secure it? Pick a strong passphrase of over 20 characters with upper, lower, special characters, spaces. Everyone forgets about spaces, and that changes the game, adding a space to your passphrase. Disable WPS and encourage your users at their homes to not use WPS. If you have to use pre-shared key, limit who has access to the pre-shared key. And ultimately, move away from using pre-shared key, if at all possible, into WPA2 Enterprise with some EAP types that your infrastructure supports. And ultimately use an EAP type that makes the most sense for your organization. And we'll be talking about one that is a common path coming up here right after you work on lab. All right, so lots of stuff that we talked about: crack, WPS, pixie dust, key selection, you name it. So lots of things for us to consider here. Time for lab. Let's take a look at attacking WPA2 Enterprise and specifically taking a look at PEEP as a great beginning steps for organizations to move into picking an EAP type that is largely supported across their enterprises. There is some issues with using EAP as your EAP type, largely due to client configuration. But if you have some pretty decent control of your clients in the organization, you can actually deploy PEEP quite well and be not subject to some of the attacks that we're going to talk about. First, we're going to look at how sort of PEEP works and then how those attacks can be implemented. So we're going to put all those pieces together. All right, we're going to talk about PEEP as our EAP type for an authentication protocol, and how PEEP does authentication and ultimately PMK distribution so that we can do encryption of our data, just like we did with pre-shared key, but having a lot of that math pre-done for us. And less subject to obtaining data out of the air because we're not deriving it on a pre-shared key. We're deriving it in a secure tunnel after some authentication, proving that we are who we say we are to those networks. We'll look at the process for WPA2 Enterprise with PEEP, which some of the same methodologies are used to build upon for TTLS and EAP-TLS, which are arguably some stronger but more complex implementations of an EAP type, but using the same concepts as a base and just building upon those as well. But definitely PEEP is a solid choice for organizations moving into an enterprise EAP type. And then we'll talk about how specifically we can secure PEEP, which also start to roll over into some of the same suggestions for TTLS and Ep.3. We're now moving into some of the best solutions for securing wireless networks that we have for enterprise, and potentially, if you're willing to go do so, for your home as well. But we find that attackers, they're lazy. They don't want to spend a lot of time attacking these high security networks and potentially well-configured networks, or they don't have a lot of luck. So the easiest thing for them to do is go for the low-hanging fruit. So observe where machines in the enterprise are and see where they've connected to other networks on the planet. We've discussed this a little bit with iSniff GPS. We talked a little bit about this with Kismet, with the auto group probes. But that data was not really easily parsable outside of Kismet. So leveraging the PCAPs from Kismet, or with new Kismet SQLite3 converted to PCAPs, we can visualize what devices have connected to what networks. We can observe that Larry's laptop, Hokusai, has connected to secure enterprise network, WPA2 Enterprise with Ep.3 or PEEP, and it did so securely and didn't fall victim to any of our attacks. However, Larry takes that machine home every day, and he does some report writing when he leaves the office and checks some emails and does a couple of spreadsheets. But he takes that home and connects that to his web-enabled network at home named Larry Home. And yeah, I said WEP. And why WEP? Well, maybe my kids are really into retro gaming, and they've got one of the old Game Boys that the best encryption that they would support was WEP. So now I have to dumb the whole house down to WEP so that they can use their Game Boy on the internet. So thinking about the attack path, if I'm a relatively determined attacker, it may be easier for me to attack something at the lowest common denominator, or a significantly easier network where your devices roam to. And let's figure out where they've roamed to by looking at those probe requests. So do some sniffing, grab some data, and look at that auto probe group within Kismet. It's really hard to look at and parse, but we can use that PCAP data with AeroDump to read it in with AeroDump and output it to a CSV file, so some conversion there, and then use the Airgraph NG tool to output those to some more human readable graphs. That, hey, we had a network that was observed, and we saw these devices probing for that network. Hey, Sec542, are you there? And also these other networks. Now we start making some questions to say, like, Wiggle for these unique names, and where are they, and what security settings do they have? So looking at this one, we have this one device here based on this MAC address that is connected to the employee network. Maybe that employee network is WPA2 AES CCMP with properly configured PEEP with appropriate certificate trusts. Good, pretty darn secure. But it's also connected to the Sec542 network. Similar, if we had one here, it's a pre-shared key network that we told everybody what the key was at the beginning of class, and maybe we can find somebody that's willing to share that with us. Maybe this is an open Linksys network. Maybe this is ATT Wi-Fi at Starbucks. Now go find someplace else to interact with this machine. So it gives us a graphical representation of those probes that we saw in Kismet that were hard to parse. And using the common probe graph here as the graph type, it will also do the client to access point relationship graph, or the CAPR. So Airgraph is great. It does some nifty charts. I still use it quite a bit. Airgraph is kind of a pain to install if you haven't figured it out, but once you figure out the install problem, it just doesn't copy one file where it's supposed to in the install script. So once you get that figured out, it's as easy as either creating a symlink or moving the file like up one directory. There's a successor to that called Beacon Graph. Airgraph is potentially going to run into some problems with some of the new packet capture types, with PCAP-NG and all sorts of that type of stuff. But Beacon Graph, under active development from one of the former students of this class, saw that Beacon Graph was kind of ugly and said, we can make this better. Using, what is it, the Neo4j engine that Bloodhound uses to do all of its rendering. I had struggled a little bit to get some of it installed because his instructions weren't particularly great, but based on our feedback, he's updated the instructions for doing so. Takes the output from AeroDump CSV and gives us the ability to render similar types of drawings in a really modern interface to give us those same sort of graphs that look much better when you include them in a report, because nice and colorful, high resolution, and easily readable. He's also looking at looking at adding support for additional types of inputs from some of the other tools as opposed to just the CSV. And it was quite amazing in that the gentleman in class, he was in class with James, one of the other instructors, and he said after class that day, said, "Hey, the Airgraph was pretty neat, but man, is it ugly." So I'd love to do something new. And the next morning he came in and had Beacon Graph done. James made him show everybody what Beacon Graph looked like. And now it's pretty cool. It's a heck of a lot nicer looking than Airgraph. So we went for the low-hanging fruit. Maybe we didn't have much luck there. Let's do it the hard way. All right, let's take a look at PEEP. Let's talk about how PEEP works so that we can understand some areas in which we can attack it. Okay. The intent with PEEP was the ability for us to take away the user-defined input for those keys and use another mechanism to authenticate that I am a permitted user of the wireless network. And if I'm a permitted user of the wireless network, we'll have the wireless network and its infrastructure assign me strong keys over the air in a secure fashion. To me, this automatically sounds terrifying in that you're going to provide me keys over the air and in a secure fashion? What could go wrong? Well, there are a few things that can go wrong. There's also a few things that we can do really well. So we're going to authenticate to the network, username, password, some certificate trusts with PEEP. Once we have those certificate trusts, we can create a TLS encrypted tunnel and then do data exchange for our key material over those TLS encrypted tunnels. We never make mistakes with TLS implementations, do we? Yeah, he says knowingly. Yeah. It's less on the TLS implementation itself. It's how the users have implemented TLS and how they've chose to trust the whole TLS implementation. And we see many, many organizations moving to PEEP away from pre-shared key. They have the infrastructure, they have the capability, and can significantly improve the security of pre-shared key because we're doing constant key rotation and we're not putting those pre-shared keys in the hands of the users. Pre-shared keys, we mentioned in the last module, limit who those are supposed to be, who you trust those to. When I was working in healthcare and I left the organization, they made me write my own termination plan. I was effectively CISO in all but name. I was responsible for all of the stuff. And they said, well, Larry, you're leaving and you're the security guy. What do we need to change when you leave? Like, this doesn't seem right. One of the first things that I said was disable my Active Directory account because that will terminate VPN, this, and this, and will largely prevent me from gaining access from the outside. The next one you need to do is you need to change the pre-shared keys on all of your wireless networks because they were only doing pre-shared keys at the time. Oh, and that one WEP network you have too, you should probably change that WEP key. Because if you don't change those keys, I helped you derive good keys for those networks. And in fact, you have allowed me to bring my Mac in my personal Mac into the organization and a documented exception for the policy because you needed somebody in the organization to help support the VPN client for the Macs on your doctors. And I was the guy. So I needed to have my Mac at work, and I offered to use my personal one. That said, you also allowed me to connect it to the Wi-Fi network, so I have the pre-shared keys stored on my machine. 1, Active Directory, 2, pre-shared keys. They trusted me with them. Changed them. Well, I left. They changed my Active Directory password. I'm assuming they changed my Active Directory password because I never tested it, because that would have been unethical for me to do so. But 6 years later, I was back at that hospital organization. We were having our second child, and our second child came 6 weeks early, and she was transferred to the neonatal intensive care unit and was there for a couple of weeks. While day 2, we go into the neonatal intensive care unit to spend some time with her, and we're going to be there for 6-8 hours. So I bring my laptop, my personal laptop. I hadn't cleared out my preferred network list in eons, like 6 years. Fire up my laptop, turn it on, wireless adapter is already on, scans for networks, and connects. Like, to the internet we go. And then I look, like, wait a minute, that means my preferred network list hasn't been cleared in 6 years. And I click on it and see which wireless network it's connected to, and it's connected to the hospital's internal wireless network, not the guest, the internal one. Number 2 on the list of my departure things to change was change your pre-shared keys. 6 years later, they were unchanged. I immediately disconnected and went and connected to the guest network and decided it was a probably good idea to clean out my preferred network list at that point. So I did. Terrifying. I don't know what the status is now. I haven't fortunately had the need to be back to that hospital, so that's a good thing. Okay. So hopefully they've moved to something better. So by going down this path, we remove that trust for users to have that pre-shared key. So we're doing it dynamically based on our authentication scheme with PEEP. With our authentication scheme with PEEP, we're providing a username and password exchange over the air that we do not want casual observers to be able to sniff with monitor mode. So we establish a TLS encrypted tunnel in which we exchange the information over. So if we sniff, we see TLS encrypted exchange. And we use the traditional TLS wheel of trust challenge response mechanism with public and private keys. And those public and private keys signed by specific organizations for specific devices in which our client devices choose to trust the validity of those based on dates and for whom they were signed for, and ultimately the certificate authority that said, yep, these are valid. I trust that certificate authority, and that certificate authority says that is good, so I inherently trust that certificate. So by that trust mechanism, challenge response, here's a value, server sends a value to the client encrypts it with its public key, sent back to the server decrypts it based on the public key. Yep, great, you had the right public key. We can now do some encrypted data with the public-private key pairs because you've trusted that public key because it was signed by a certificate authority you also trust. That's like saying, Norman and Zach are friends and Norman trusts Zach. So I trust Norman, hereby I implicitly trust Zach, right? Because you two trust each other, right? So we establish a TLS tunnel based on that certificate trust. We now have an encrypted tunnel, and now we can do some authentication exchange. So what does this all look like? Well, we go to join the network, we go to authenticate to the network, and the access point says, hey, wait a minute. We need to know who you are so that we can perform some authentication, create a TLS tunnel to prove who you are so that we know to give you keys. If you're not Larry and you can't prove it, why are we going to give you keys to join the network? So the first step is the Radius server connected to our access point for our Ep type says, hey, who are you? An identity request. And the client then responds back with an identity request of a username and or domain and a username. In this case, the identity response is sans jwrite. In the clear. Now, This one is interesting in that we don't necessarily have to do this. This is for environments where we may have multiple domains, and it is intended to perform routing so that when we are performing the actual authentication, the Radius server knows which domain to query to see if the user's there and their passwords are right. We can tell it nothing. And then it will figure out the routing later. But this was just an attempt to make it speed up that whole routing stuff. So this initial step, we're giving up a username in the clear so the Radius server can go, oh yeah, I need to go over there in the SANS domain and see if Josh's password is correct. If we give it nothing, it will still figure it out. So there's some information disclosure here in the clear for those usernames. Oh, great. Josh, we see that you are in the authorized wireless users group in the SANS domain. Here's some TLS certificate information. We'll establish a TLS tunnel. This becomes a little bit of computationally expensive exchange from the Radius server and the client. We'll go through and inspect all the TLS certificates. Are they trusted? Are they for the right devices, depending on how our client is configured? And now we have an encrypted tunnel. Within that encrypted tunnel between the Radius server and the client, it asks, again, who are you? First one was for routing. Now it's, all right, who are you? We know which directory store to authenticate you against. If you didn't provide that initial routing information, it will still do it here. Oh, I'm Sans J. Wright, encrypted over the air. We then do challenge response from the Radius server to the client. Hey, here's a value. Here's a random number. Use your NTLM hash, MSCHAP v2, to perform triple DES operation to that. Send it back to me. Radius server receives the response hashed with the user's password. They go to Active Directory or their directory store, grabs the hash of the user's password, takes the EAP challenge, does the same operation, and if they match, yep, Mr. Wright was the right user, had the right password hash to respond to that challenge, they have authenticated, typically using MSCHAP v2 with PEEP. It's typical challenge response. We have a stored password, we have a user that's entering one, does computed versus observed based on what we have in that trusted store, LDAP or something of the like, Active Directory, doesn't match. Yes, in this case, Mr. Wright had the correct password that compared to the one that was stored in Active Directory. So the Radius server issues an EAP success message. Upon success, we then use that TLS tunnel to distribute PMK over that encrypted tunnel, whether it is TKIP or CCMP. Deliver PMK, do a four-way handshake, calculate PTK. Then, after we've calculated PTK, we now have an encrypted session, we have some encrypted data. We can then trigger new four-way handshakes that we can do over encrypted packets with WPA, WPA2 Enterprise, encrypted packets. And we can reissue four-way handshakes in an encrypted fashion to rotate keys every 65,535 packets. So even if you catch the first one, you now need to decode the new exchanges and recalculate PTK every 65,535 packets, or 2 to the 16. Taking a look at this, going on more visually. We've authenticated, we've got our EAP success. The Radius server says, great, you are who you say you are. You have proven to the network that you are the correct person. You are trying to authenticate to the correct network because you've done our TLS certificate circle of trust. Here's PMK over the TLS tunnel. And then we acknowledge that, yes, we have received PMK. We can't now start encrypting data. We can't derive PTK because we have a few things that we're missing. Those nonces, the authenticator address, the supplicant address, the 2 MAC addresses. And more importantly, we've distributed PMK over an encrypted tunnel to the client, but the access point doesn't have PMK. Radius server, using Radius shared secrets over the LAN, distributes PMK to the access point. Now the access point has PMK. Now we can go and do our four-way handshake. Four-way handshake in the clear the first time. We derive PTK, we create an encrypted session for WPA, WPA2, and then every 65,535 packets in that encryption session, we can do a new four-way handshake. Now, in this case, we're doing one of those things with encryption they say you should never do, that we're deriving a new set of keys or transferring a new set of keys in the encrypted tunnel with the previous set of keys. So technically, if we can recover PMK here, we should be able to decrypt this four-way exchange to deduce these new keys, which we can then decode the next set of traffics and then cascade that on down. It is entirely possible. It's not the best, but it could be worse. All right, we've got PMK, we've calculated PTK. With this method, we're having something create PMK, distributing it over our secure tunnel, our key encryption keys over that secure tunnel. We've done our authentication over that secure tunnel. And then we can rotate those keys every 65,535 packets. So we're limited on how many packets we can get if we recover PTK for each one of those sessions, but we can then potentially cascade that if we recover PMK as well. It's not perfect, but it's significantly better than having a user-derived password that is subject to offline brute force attacks. There is no ability for us to do offline brute force attacks. We'd have to brute force PMK, which is quite large and very large key space. So where does this really fall down? Well, we've got a couple of ways. And one of the ways that I find that many folks, it's based on an incorrect PEEP implementation, and usually on the client side. All right, so initially what I do, or what we do in a PEEP-enabled network, is just sit and listen and observe users authenticate to that network first thing in the morning. And we observe that initial identity request in the clear. That in many cases, the organizations do not set that to anonymous. They don't leave it blank. They are sending the user's domain and user, or their user account that they will use in the subsequent encrypted TLS tunnel. So what do? I just sit and listen, and I collect usernames, and then I do one of two things. I then attempt to go authenticate to the wireless networks with bad passwords and lock all of the Active Directory accounts for all the wireless users. Denial of service condition. That makes them unhappy. Or more importantly, I make some very educated guesses about the username formats, and maybe I scrape their websites and compile more users that might use the wireless network, or just take the ones that I have and do password spraying. So instead of brute force passwords and get the account locked out after a couple of guesses, I'll make 1, 2, maybe 3 guesses of a well-chosen password based on how we know humans react to password changes and times of year and so forth. We can use a tool called SniffAir to automatically take a list of usernames and do password spraying against a wireless network to guess passwords for those users. We typically use password spraying for something against like Office 365 or against a VPN or some sort of web application. We now can do the same for wireless networks. Take a list of users, guess 1 or 2 well-chosen passwords. In this case, looking at this one, the password we've chosen is summer 2018. As when we wrote this slide, it was about summer of 2018. It was the right season. Maybe we'd be looking at summer 2019 now. Maybe even consider summer 2019 with an exclamation point at the end. Like, your help desk changes the password for a user, and do they have some tool to pick random passwords for them? Yeah, typically no. They pick a password for everybody, and it's usually based on season, year, and one uppercase character. It's easy for folks to remember, and sometimes you're not forced to change it. Okay. So in this case, using SniffAir, we're using the auto-eep method. We're using our wireless LAN 0 wireless interface, not in monitor mode, because it's going to act as a client. We're setting the SSID that we want to connect to. We're setting the encryption to PEEP and key management to WPA EEP. I had to ask the question because their language here was a little bit obtuse. Okay. We're setting a password to guess for all of our users, summer 2018. And we've got a bunch of users that we've collected from phase 1 manually in the clear in a user text file. And we need to specify the full path to that. And then Metasploit-like, we tell it to exploit and go. It then goes and grabs the first user from the user list and tests Summer 8 2018 for that password. And it worked. I now have Josh's password. Thanks. We moved on to my password. It wasn't Summer 2018. Mike Poor's password wasn't 2018. And James Lidi Vidal's password was Summer 2018. Damn it, James, change your password. You should know better. And this is a little bit slow because it is doing active attempts against the wireless network to authenticate with these users and tries multiple times, okay, just by nature of PEEP. So it's not terribly fast. However, what I did, we had 15,000 users to test on a recent assessment. So I took 4 Raspberry Pis, 2 wireless cards apiece, and set them to on boot to run sniff air with the list of usernames split 8 different ways, and left them in their office overnight. And it finished all 15,000 usernames by overnight. The problem is I picked the wrong password. It was like summer 2019, and their password policy included a special character. They said if I had done summer 2019 with an exclamation point, I probably would have gotten 50 or 60 users. Damn it. In telling this story, the authors of SniffAir now made it so that we can do this in a multi-threaded environment with multiple wireless cards. So I didn't need 4 Raspberry Pis. You can do it on one with multiple wireless cards and it will use all of them at the same time. So plain text usernames to do denial of service-based attacks or password spraying. Some other things that we find with failures with PEEP is improper validation of the TLS certificates. Radius server passes a TLS public certificate to the client, and the client is left to deal with, hey, do we trust the certificate or not? And then if they decide to trust it based on various rules or various client configuration, they'll then provide credential information to the Radius server. In an ideal world, we should only be accepting certificates from that Radius server that match all sorts of capabilities so that we'll only ever accept really good, valid certificates. But what many implementations fail to do is that they don't trust or they ignore that the certificate was signed for www.sans.org when it really should be for radius.sans.org. They don't care that it was signed by a self-signed certificate authority or was an internal one because they never set up that trust for that signing authority. They make all sorts of other mistakes about trusting that initial certificate. So what do? As an attacker, I try to abuse those misconfigurations in the way the clients choose to accept those server certificates. Okay. So it's all based on the server certificate validation. Was the certificate signed by a certificate authority I trust? Did it match the common name of the server that sent it to me? Many cases we're finding that these are improperly deployed on the clients. The server certificates are generated well with good certificate authorities, even if it's their internal one, but they fail some way in that circle of trust to get the certificate. So what do? I try to create my own. I sniff 4-way handshakes. I observe the public key from the certificate exchange, and then I try to replicate my own server certificate on my evil access point that closely mimics the real one. It will still be invalid because I signed it myself. It didn't come from a valid certificate authority, but a great social engineering attempt against the users. So thinking about some of the ways that these certificates are used with PEEP, what I find happens is that we have multiple distinct groups working on the wireless deployments. We have our wireless admins, and then we have our Active Directory admins, and maybe those Active Directory admins are the ones that created the certificate authority. So they create us a certificate, but they never added that certificate authority to all the workstations to be trusted automatically through group policy. So we've got a certificate, we've got a client, and we keep trying to authenticate to the network, and it's giving us certificate errors. So as the desktop person is trying to get it connected to this wireless network, we go through and we start unchecking boxes for our PEEP network. And we uncheck the verify the server's identity. Meaning, in this case, if I receive a certificate from the Radius server, I will happily accept any certificate you give me as valid and will accept it for this connection. This now becomes trivial for me to exploit because I can use on my evil wireless access point and Radius server a snake oil signed certificate. I can put whatever values in I want, and the client accepts it. And then what happens? The client accepts it, creates a TLS tunnel, and then provides me username and password. Thank you very much. Typically, the verify the server's identity is checked. We'll explore some of the other connections as well. Look at this. Enable identity privacy. We send the username and password in the clear on first step, not unchecked. Unchecked by default. No, sorry, username in the clear. Looking at Windows 10, when we're presented a certificate and we have some of those checking, it's asking us, hey, do you trust the certificate? We're relying on the user to make some decisions. With Windows 10, you find the wireless network, you go to click on it, you go to join the network, and it said, hey, what's your username and password? Username and password, click OK. But now I'm authenticating to a network that I can't validate is the actual one because I've never seen the certificate. Now, with Windows 10, it takes the username and password and doesn't actually do anything with it just yet. Holds on to it. Goes and gets the certificate, and then displays you the certificate. Hey, here's your certificate. Would you like to continue connecting to the corporate network? Okay. If you expect to find it here, cool. Go ahead and connect. Okay. Otherwise, it might be a network with the same name. Okay. Expand certificate details, and this is what we get. Can we tell if that's a valid certificate from the information provided to us? This is the most information they give us. Oh yeah, heck yeah. The fingerprint's totally good. Has anybody ever compared server certificate thumbprints? You're probably the only one that I've ever seen that's done it. I don't even do it, right? Like, yeah, that's like having the PGP key, the signature block on the back of your business cards. That's totally cool and geeky. Has anybody ever actually validated one of those? So, do we know that that certificate came from the legitimate network? Don't know. So we continue to connect because I surely expect it to be here. iOS, similar types of things. Asks you for your username and password, doesn't do anything with it, then goes and gets the server certificate. Okay. It's a VeriSign Class 1 public primary certificate from the example certificate authority. Seems legit. Sure, we can get more details. Okay. But in this case, what are our options? Trust, don't trust. No, we have trust and cancel. And when we do cancel, that means we get disconnected from the network and I can't get to Facebook. I'm not sure with the absolute most latest versions of Android, but Android suffered from some problems in that they trusted no certificate authorities by default. So they implicitly trusted everyone. So no matter what server certificate you gave them, would happily be accepted on the devices, regardless of how you, unless you went and did some specific configuration. The big configuration issues with PEEP deployments end up around the client configuration, in that we get the clients to receive the TLS certificate, and in many cases, the users are left to make the decision as to whether or not to trust the certificates as presented to them. So as an attacker, I would stand up my own solution and provide a certificate and try to lure the client to accept my certificate and have it match as close as possible. Now, the client configuration can give us many options as to how to involve the user in making those decisions and or automatically accept certificates with some specific parameters as to how they should be trusted. Now, when we involve the user, users make really good decisions about security, don't they? Yeah, you laugh, yeah. Not usually. Sometimes they do. We would probably make some good decisions, but we're smart folks. We're IT professionals. We're security professionals. Many users do not have the same level of smarts as we do, and they're ignorant. So they will often be presented with a certificate. They will accept the certificate for an invalid certificate, which is potentially tied to a rogue access point, and then they will type in their username and password, or it will happen automatically. And once that TLS tunnel is established with that bad certificate, the credential information is given to the attacker. So how can we make this happen? Well, we've got a couple of different ways. Ultimately, we're using some of the tools output or in conjunction with host APD-WPE. You had a little bit of experience with the fuzzing with host APD yesterday. It's a software application for taking a wireless adapter and turning it into an access point, however we choose to configure it. With host APD-WPE, it is intended to be weaponized to tie it to our own copy of FreeRadius, which we have modified to with a patch to log all of the credentials given to the Radius server, either to a file and or the console. So stand up an access point with a certificate, get users to connect to it. It says, hey, we need your username and password for this PEEP network. And you type your username and password in, and it goes to the Radius server, and then the Radius server logs it for us. With host APD-WPE gives us all sorts of tools for doing automatic creation of certificates, creation of access points, and can give us the ability to patch the version of FreeRadius to do that logging. And lots of wireless adapters will work with this, the one that you have in your kit, as well as that AWS 1900. Okay. Any idea what the WPE of host APD WPE stands for? It's the Wireless Pwnage Edition. All right, pretty easy to install. Apt-get update, install a couple of SSL libraries, and then pull some patches from the Aircrack repository. They are the better of the group for host APD. Grab host APD, extract it, patch it with the Aircrack NG set of patches, make host APD, and then use the bootstrap script to create some certificates. And we can set the certificate settings to be whatever we want within the config file when we make those after the install. So we can tailor the country, state, organization, you name it, to be that of the ones that we have observed of the legitimate network that we are wishing to attack by observing four-way handshakes and that key exchange. The TLS certificate exchange when legitimate users are coming into the environment with Wireshark, and Wireshark can even dissect all of those certificates for us. What I'd really love to see here is if we could have a tool that if we captured that, we could automatically go into the packet capture and have it extract the certificate for us, extract those fields and populate a config file for us so I didn't have to do it manually. Let's automate the process. And I've been asking for this for a long time. And I've even tried to do it with various degrees of success with T-Shark and some of the others. And then I got down a road and I broke it. But I found a couple of other tools that were really close on making it work. And I was playing with those last week. One of them was Creep, so C-R-E-A-P. It's a Python script, and I think that one was one that was trying to do certificate extraction on a network where I knew where their certificates were being exchanged. It didn't actually extract them. So maybe I'm just using it wrong. So create our certificate. Let's use airmon ng check kill to shut down any of the processes that may be interfering with the use of our wireless adapter with host apd-wpe. And then run host apd-wpe from within our build directory and using the default configuration. We can edit that to be whichever access point names we want, such as that of the corporate SSID using PEEP. We'll start up an access point using our wireless adapter, and we'll create that access point, and then we use a device to connect to it. And it will ask us certificate trust, username, password, and in this case, we've plugged in a username of jwrite, and it has recorded the challenge response mechanism for MS-CHAP v2, and formatted those so that we can pass those right to John the Ripper, and with little modification, send those to Hashcat as well, so we can start cracking passwords. Sometimes I've found that building these configurations, depending on whether we want 802.11, BGNAC, specific channels, specific feature sets, manually is quite obtuse because the fields that you need to fill in aren't exactly what you expect from the host APD configuration file. But I've found that a tool called EPAMmer by Gabriel Ryan can really help automate some of that process for creating those host APD config files. It will also stand up host apd-wpe for you in an automatic fashion, and will create certificates in all that type of stuff in a more automated fashion. You can also use EPAMmer to save the config file so that you can use it in a repeating fashion, so you don't have to go through that automated setup every time. So I've found some great add-ons for host apd-wpe with EPAMmer to help aid in creating those config files and even some of the certificates. So now once we have credentials, we have a username, and we have MS-CHAP v2 challenge response, we can now go and crack those. One of the ways in which we can do so is with a tool called Asleep and a word list, providing those challenge response mechanisms on the command line. It will attempt to go through MS-CHAP v2 challenge response mechanism for all of the words in our dictionary, and will return success if the word for the user's password was in our dictionary. Asleep had some interesting background. It is a dictionary-based tool, CPU-based, and was written with the intent of breaking Cisco Leap. As we talk about doing MS-CHAP v2 with PEEP in an encrypted TLS tunnel. However, Cisco Leap would do MS-CHAP v2 in the air with no encryption in plain text. So you just sit and listen, you get MS-CHAP v2 credentials, and then you just go crack them. Fortunately, Cisco has deprecated Cisco Leap, and I don't see anybody using it anymore. But the tools that came out of that do still have some utility. We can also continue to move down the path for additional tools. We can use John the Ripper to do wordless-based attacks against these as well. And of course, we can also send these to Hashcat. So thinking about how we need to make our clients secure, specifically looking at Windows, because it's arguably the easiest to sort of explain what we need to do. Now, the failure really comes down to the clients and how they do the certificate trust and how they interact with the user. So We want to make sure that validate server certificate is checked. That's the default settings under Windows. Hey, is this a valid certificate? Yes. If it's not a valid certificate, reject it. So we want to make sure that it is a valid certificate. We then want to make sure that the certificate presented to our workstation is signed by an appropriate certificate authority, and only one or two certificate authorities. In this case, we've selected the VeriSign Trust Network. We could have this be our own internal certificate authority sent to our workstations via group policy. Select the one, whichever one is appropriate. If we only stop there, if we only trust valid server certificates and ones from the VeriSign Trust Network, I can go and get a certificate for hacksthematrix.com from VeriSign, have it be valid, and present that to the client, and the client will say, oh yeah, it's a valid certificate, signed by VeriSign, good to go, accepted automatically, no interaction from the user. We need to do some more. Not only do we want it to have it signed by a trusted certificate authority, we want it to be issued to a bunch of servers, a primary, maybe a backup, the CN or the common name of the server that this certificate was issued to. In this case, only accept server certificates from these two servers, radius1 and radius2.sans.org. So we will only accept a server certificate that is valid, signed by VeriSign for radius1 and radius2.sans.org. If you are given anything else as part of this process, do not prompt the user to make any decisions about any other certificate. Take the choice away from the user. So if you get something else, radius3.sans.org, don't prompt the user to say whether this is good or bad or ugly. If it's not signed by VeriSign, don't give them a choice. If it's not matching the common names, don't give them a choice. If it's an invalid certificate, don't give them a choice. Take those out of the hands of the user, because users make good decisions. No, they don't. And finally, enable identity privacy. And in this case, we've chosen to use the username of anonymous. It doesn't matter what we put here, and we can in fact even leave it blank. This is merely that first step when we send that in the clear, so that the Radius server knows where to route to which directory to route its request. It will figure it out on the second half if we don't include it. So don't allow usernames to be harvested in the clear. All right. The big one here, the clients are the ones that are typically at fault. We can build our infrastructure with appropriate certificates. It's how the clients have chosen to trust them, and or whether we've given the user the ability to make decisions. However, in any of these cases, to try to lure users to bring their device to my evil access point with your corporate SSID that is not in your inventory, tied to my evil Radius server providing a cert that isn't signed by the appropriate certificate authority, and the users make decisions. I have implemented a rogue access point in your environment trying to lure your users. Now, what did we say on, what was that, day 1 about rogue access points? What's worse than a rogue access point in your environment? Yes, a device on that rogue access point. If I have an evil attacker in that environment with my rogue access point, and you let a client connect to it, in this case, that client is connecting to my evil Radius server and providing me credentials, which I can now crack and then use internally. This gets worse. For me, from a pen test perspective, if I get credentials that are typically tied to Active Directory on the internal network, now not only can I get on the wireless network, I potentially have credentials to other Active Directory resources, so I can start querying the domain, running Bloodhound, get access to other applications, maybe Office 365. Heck, maybe they even work on the VPN. Yeah. Maybe they don't have two-factor authentication. Maybe I have the ability to disable two-factor authentication with some of these credentials. So the possibilities now open up even further. The big one here is we have the ability to detect a rogue access point in our environment with wireless intrusion detection. And I highly recommend that we configure something like this for wireless intrusion prevention, because no one in your environment should be standing up an access point that has the same SSID as your network. If that happens, something bad has happened or is about to happen. perform denial of service attacks against that access point and the clients to prevent them from connecting. That wireless network that I got, that I didn't get in, that was absolutely the best secured network that I've ever seen. We stood up rogue access points. They were using PEEP. They had appropriate certificates. We wanted to see if we could get users to accept them anyways. That was sort of where they fell down. But they had wireless intrusion prevention. Every time a user tried to connect to us, disconnected. Would do deauths against it. So we never got credentials until we went out to the far end of the parking lot and got people coming off of the bus with their mobile devices. Because it wants me to authenticate to the wireless network. I was outside of the range of the prevention. And they would happily accept certificates that were not properly signed. So we talked about PEEP using TLS to protect our inner authentication, our username and password, using this circle of trust to create a encrypted tunnel. Then once we have that encrypted tunnel, we can do some authentication. Post-authentication, having the Radius server distribute PMK over that encrypted tunnel and over the LAN to the access point so that we can then do a four-way handshake, create PTK, and do subsequent four-way handshakes in the WPA2 encrypted tunnel as well. We talked about some man-in-the-middle based attacks. We talked about authentication attacks for password spraying. We kind of missed the key distribution attacks. If we think about PMK, how they're distributed on the LAN, there's a possibility if we already have access to the wired network, we could potentially capture PMK distribution via Radius protocol to the access points. This becomes chicken-egg problem. If you want to get access to the wireless, you need to get the PMK off the LAN, which means you need to be on the LAN already. And if I'm already on the LAN, why do I need access to the wireless? So it's conceivably possible. And thinking about improving WPA2 Enterprise, it really comes down to configuring your clients appropriately. Windows is fairly easy with GPO. We can do similar types of management on the Mac with some third-party solutions as well as Apple's solutions as well. The challenge becomes looking at Android and iOS. Specifically, the wireless settings are often the control of the user, and if you allow users to bring their own devices into your network using that authentication, you don't have a lot of control over how they configure it. You can configure these settings on both Android and iOS using some sort of mobile device management of all its varieties, but now you have to convince users to potentially allow their personal devices, at least in some capacity, to be configured by your corporate stuff. And I know many users who are very hesitant about that. Time for you to work on lab for both identifying vulnerable clients. This is using Airgraph NG. And then attacking WPA Enterprise. First one, you're going to generate some of those graphs to find the low-hanging fruit. That should only take a couple of minutes. And then second, you're going to actually stand up host APD-WPE, and it will create a wireless network for you. Please pick a unique name so that you can tell it's yours. And then take a mobile device or have a friend, ask them to authenticate to it and accept the certificate as given. Have fun generating that certificate. Distinctly moving outside of the Wi-Fi realm. We're moving into other protocols, other frequency ranges, and other technologies. However, when we start going through some of these, we're going to see some similarities in these protocols to others as well. In the way they do authentication, the way they do encryption, hashing algorithms, and how they're doing some of their security implementation, while some of the protocols, the packets themselves, may be very different. A lot of the same concepts do apply. And one of them is digital enhanced cordless telephony. So let's take a look at DECT. We're going to talk about where DECT is in use, some of its operation, We sort of tip our hat already about some of the issues that we're going to see with DECT, about the security implementation and other follies, like there's some humorous stuff here that isn't particularly good, and then talk about some of the attacks that we can leverage against DECT. So a little bit about DECT. It's a standard voice and data protocol sponsored by the European Telecommunications Standards Institute, or ETSI. It gained its popularity in Europe for voice and some data applications, and is largely popular here in the US, specifically for voice. In many cases, we see this in the consumer market for residential use for cordless phones, as well as for headsets in lots of call centers for either the internal IT teams or for consumer-facing help desks and so forth. So thinking about why DECT excels, looking at cordless phone telephony as it evolved, there were lots of competing standards and or proprietary implementations that maybe weren't good stewards of the RF spectrum. They consumed a lot of the 2.4 and 5 gigahertz bands, or didn't use enough. They overlapped with other signals, caused lots of issues bandwidth-wise for wireless networks. The proprietary devices didn't have any expansion for moving forward. But DECT, with its standards-based approach and outside of the 2.4 and 5 gigahertz ranges, really became attractive for both voice and data in some cases. So DECT, largely here in the US and in Europe as well, a voice communication for cordless phones. And one of the things that I think is interesting, I've done a decent amount of teaching in Europe. And for example, here in the US, with some of these, the hotel conferences and so forth, and the hotel staff, everybody has one of those two-way walkie-talkies. In Europe, I've been to Berlin and London, and a couple of other places, Amsterdam, that all the hotel staff and the conference staff have DECT phones. You need something, you pick up the phone, you go through the address book, and you call someone, and it's a phone call direct using DECT. And they've got DECT access points all over the facility. So instead of doing more of that broadcast medium with the walkie-talkie, you're having a more personal communication, and potentially even do that by group. So while it may not be popular in homes in some cases, there are some enterprise applications for it as well. And Kane asked earlier, what's the difference between all of the versions? Well, there's only one version. It's dubbed DECT 6.0 here in the US. And think about the evolution of cordless phones. We had 900 megahertz, and then we moved to 2.4 gigahertz cordless phones, and then that area got crowded, so we moved to 5 gigahertz. So what's better than 2.4 and 5 gigahertz? 6. It's not 6 gigahertz. It's just the indicator that 6 is better than 5. Yeah, it's a marketing thing. And there is, quote, only one version. Yeah, so kind of neat. Kind of terrifying, too. Lots of devices available. And I'd argue the DECT forum says they probably have a few more than 820 million devices. But we're starting to see the reduction in DECT stuff in the consumer market, given that how many people still have a landline phone in their house? Like one attached to like plain old telephone service or FiOS. Am I the only one? Wow, all right, that's a first. Usually there's like myself and one other person. I still have a landline phone. It has a DECT phone on it. And that's the phone number I give to all those places. It's like my spam catcher email address. You just go sign up for stuff on the internet and you use that one email address. It's just spam. You don't want any of that garbage. That's the landline. Looking at the architecture, we have some similarities and differences to a wireless network with DECT. We have the fixed part, or the FP, which is kind of like the base station or the access point that we'd see in Wi-Fi. It does a broadcast of its presence using RFPI. Hey, I'm here, I'm a device. Kind of like a beacon frame with Wi-Fi. And then we have the portable part, or the handset, otherwise known as the PP. This is the slide where I giggle like a 12-year-old boy, because we're going to be talking about the PP for a little bit. Okay. I know, totally inappropriate. Why couldn't they have named it something else? Okay. The portable part scans for RFPI advertisement, listens for beacons, okay, selects the best fixed part based on signal strength and its capabilities. Oh, hey, kind of like beacon frames and clients picking the one with the strongest signal strength and the matching sort of security settings. However, the difference between DECT and a Wi-Fi network in a similar type of architecture with a base station and a client is that in Wi-Fi, the access point is the one that is defining the security for the communication. With DECT, it is the portable part that is the one that is responsible for negotiating this, the encryption and or any security on a per device basis. With each one of these fixed parts, the base station, we can potentially support up to 12 concurrent phone calls. And we can see how this happens with some of the math. It's really easy math that I can do. Okay. What do the physical layer characteristics look like? We use the 1.88 to 1.9 gigahertz range in Europe and 1.92 to 1.93 in North America. So we have double the available frequency range in Europe as we do in the United States, so giving us more channels available. So we have 5 channels available between 1.92 and 1.93 in North America and 10 channels available in Europe. Double the width, double the amount of channels. We use one channel at a time. We can hop between those channels if we so choose, but at any given time for some communication, we use one channel. Each one of those channels is divided into 24 slots. Okay. So 24 individual components for each one of those channels. How do we use those slots? Well, a voice call uses 2 slots for full duplex communication, one up, down, one for transmit, one receive. Data can use all of them for up to 532K of maximum bandwidth half duplex. So this is some really easy math. A fixed part can support up to 12 concurrent calls. We have one channel, 24 slots. Each call uses 2 slots. 24 divided by 2 is 12. That's just math I can do. Okay. Many years ago, I asked some folks in class, hey, who still has a landline? And how many have one landline? And a couple people raised their hand up. Okay. How many have 2 landlines or more? And 3 people had their hands up. And I'm like, oh, okay, cool. I have one landline. It's okay. How many do you have? He says, I have 2. Oh, why do you have 2, if you don't mind me asking? He says, home phone, fax machine. Oh, okay, dedicated fax machine for his business. All right. Anybody have more than 2? 2 people have their hands up. How many do you have? I have 3 phone lines. You have 3 phone lines in your house? Yep. Home phone, fax machine, teenage daughter. Oh, got it. She doesn't have a cell phone. She has a house phone instead. Got it. And then more than 3, the guy still has his hand up. 4, 5, still has his hands up. I'm like, all right, I'm going to cut to the chase. How many do you have? He says, I have 12. Wait, you have 12 phone lines in your house? He says, yeah. Do I want to ask, like, did you run a sports book or something? Or either way, you could in fact take all 12 of those lines and pipe that through an appropriate DECT fixed part and support 12 concurrent calls. That's kind of cool. Why do you have 12 lines in your house? He said, well, actually, it's kind of a little bit of a sad story. I'm like, oh man, I shouldn't have brought this up. He says, I use these 12 phone lines for my business, and unfortunately, my business folded. But because I'm under contract for the remainder of the year, I have to pay for these lines in my house for another 8 months. I'm like, oh man, that kind of stinks. What did you do for work? He says, oh, I did robo-dialing. I'm like, you! I don't feel so bad anymore. Yeah, it was at the point when robo-dialing became illegal, so he literally had to shut down his business because he couldn't get the appropriate, licenses and permissions that he needed to, so he just had to, shut it down and got stuck with the phone lines for another 8 months. So let's talk about the security for DECT. What the European Telecommunications Standard Institute wants you to know about DECT security. Absolutely nothing. Okay? They don't want to tell you anything about the security implementation. In fact, if you want to know about the security implementation, you need to sign a non-disclosure agreement with the DECT Foundation, in which they are very strict about what you can talk about. They'll give you the specifications, and it costs a ton of money to license the spec for them. So they don't want to tell you anything. All right, let's go back to looking at what we were able to learn about DECT, some of its security. Okay. Looking at the authentication through various reverse engineering and slow release of some of the documents and lots of investigation into the protocol by others. We were able to learn that DECT does perform some authentication and encryption. They have their own standard for doing authentication called the DECT Standard Authentication Algorithm, or the DSAA, which leverages PIN-based authentication between the fixed part and the portable part. On the first time we join the devices together, we get them connected to the network. We're asked to put in a PIN on one or more of the devices, which we use that PIN to derive a user authentication key using the DECT standard authentication algorithm, using the DECT standard cipher, and then we store that key for subsequent communications. This kind of reminds me of WPA2 pre-shared key, in that we're using something that a user is deriving to authenticate. Yeah, we had the PIN both the same on both ends. We're going to use that as input to derive a key, which we'll store so we can keep that authentication every time. What I did find was that, hey, these standard things, when I was doing webcasts with my phone, I thought I'd just grab this handset and pair it to my setup of DECT phones at home. I couldn't get the two to ever pair because what I found was that many of the manufacturers are using fixed pins on their devices. And a fixed pin across all of their devices. So Uniden had one set of fixed pins, Panasonic had one set of fixed pins, which is kind of terrifying because now all I need to do is potentially buy a Uniden phone to start pairing with other Uniden devices. So shared across, potentially hundreds of thousands of devices. Okay. So use a PIN, do some math, and then store a key for subsequent authentication. We derive those keys with the DECT standard cipher. And following authentication, we use that user authentication key to derive some encryption keys for encrypting our data in transit. Now, we don't have to do any encryption. The generic access profile, or the GAP, encryption is specified as being optional. The devices will authenticate to the network, but may never derive keys or use the keys. It is completely optional. And this is why I find that it's important for us to audit DECT, especially in environments where we may be talking about sensitive information over them. Because in many cases, specifically on my two sets of phones that I own, there is no indicator on the portable part or the fixed part as to whether or not encryption is enabled, or if you can even turn it on and off. And I found one set of devices that I was testing with where it said that it was turned on, yet we listened to the traffic using some of our attack techniques and it was in plain text. We could hear the audio conversations because it never applied those settings until the phone was rebooted or the battery was removed. And how often does that happen on a cordless phone? Because you always keep it on the charger. So almost never. We did some playing with that. So encryption with the DECT standard cipher uses 128-bit key length. And every time the portable part connects to the base station to answer calls and so forth, those keys change. So per session, very similar to WPA2, every time a wireless device joins a network, they do that four-way handshake to derive per session keys. You disconnect, those keys are no longer valid, you renegotiate keys every time. But with that user authentication key as some input based on that PIN that we've stored. We have a group, Team Detected, out of Berlin, that did a lot of research into the security of DECT, and they were the ones that largely started telling us about the DECT standard authentication algorithm and the DECT standard cipher. They also built a suite of attack and audit tools for us to use. There is still a lot of research ongoing with Team Detected and others. And we want to talk to you about some of the tools that are available for doing so. The Team Detected's suite of tools became a Type 2 PCMCIA card from Dashimand, the Com On Air variety, which was rebranded as the Ascom Voodoo or the Greengate DA 099. Same hardware, just rebranded. Unfortunately, Dashimand has discontinued these devices for quite some time. For we can still find them on eBay and such at somewhat reasonable prices. The problem then becomes we need to have a laptop with PCMCIA in it. How many of you guys have a laptop with PCMCIA in it right now? Every once in a while, someone has one. I have a couple machines at home that do. Okay. You have to have one of these cards, which can be difficult to find, and there's a bunch of different varieties, and not all of them work as expected. So some limited availability for this stuff. But they've got some really neat set of tools if you can get a hold of one of these. So let's go get their suite of tools from their SVN repository. For many years, for about 2 years, their SVN repository just disappeared off the face of the planet. And I would be telling my students about this stuff, and they're like, hey, where can I get the tools? Your SVN repository is down. Like, I happen to have a machine that has a copy of the code that's a couple of revs back, but it still works great. So I'll take that and I'll put it in my GitHub repository, full credit where credit's due, so at least the code is still out there. That's like you put something on the internet, somebody in their basement still has copies of it. Yeah, I was the guy in the basement that still had a copy. So we did have it go down. Another time was down for another 6 months or so, and it's back. Okay. So grab the code from their SVN repository, get the kernel source, creation of some kernel modules, add the kernel modules to our system, and then manually make our device on disk for us to interact with. We can do some scanning for devices with the subsequently compiled software from Team Detected with DECT CLI. Run DECT CLI to interact with our Dashimand card, and we set the band. It ends up in the European bands by default, because they're a bunch of Germans. They're using the European band. Makes sense. Also has support for the US band, so we change the band with band. And then we go for the gold. We automate everything and hit auto record. And auto record will start channel hopping and listen for fixed parts beaconing RFPI, and then looking for portable parts connecting to those fixed parts. And we'll lock onto those particular channels and then start recording that data to disk in a libpcap formatted file. You can stop that at any time during the conversation, and it will save those files outbound. If the call terminates, it can also tell that the call terminates on its own and it will stop on its own. The problem here is when you do auto record, it will record the first call that it finds, which you may not have permission to record. So be careful about this if you're doing testing with some of these tools. There's some more refined ways in which we can determine the call that we're going to record. They also have DECT Shark, which is like a pseudo Wireshark-like interface. I find it buggy. There isn't a lot of documentation, and I personally find it of limited use. We do need to patch it to support the US bands because it only supported the European bands by default, and then compile that with those patches and run DECT Shark. It gives us initially a list of all of the RFPI advertisements by doing some channel hopping. If we hit up and down to select the various RFPI advertisements, we can hit enter to select the network, press S to stop channel hopping and capture traffic. And it will tell us which one of these slots are in use and are using data on either the A or B channels for each one of those. I've never seen any data come out of this recorded to PCAPs. I use this more as a discovery tool than anything else. So arrow keys S and Q are the only keystrokes that I know with this tool, and there is no documentation. We have PCAPs outbound from auto record. We can pull these into Wireshark and inspect them in Wireshark. Wireshark does know how to decode them and can give us some of the data from both our A field and B field. And typically the B field is that of the voice digital transmissions in the air, depending on whether they're encrypted or not. So if we could take the data from the B field and split that out to a file, maybe you could actually start listening to some of the data. And this is important because we may never know whether some of these DEC devices are encrypted or not. That may not give us any indication, or if they do, it may be incorrect. So capture some data. Let's see if we can decode the data and listen to those voice transmissions. Just be aware that make sure you have permission from the actual users, depending on your jurisdiction, to record these calls. And we'll use some tools to extract some audio data to see if they're encrypted, and some ways in which we can more accurately record phone calls that were permitted to do so. In order to do the audio extraction, we need a couple of other tools. DECT uses G72 of either 1 or 6 audio codecs for their audio encoding. So we need to grab a decoder for that and get that installed. And Josh has also created us a script so that we can use a couple of different tools to extract the B field data, concatenate it to some files, and then automatically use the audio codec utilities to convert the raw data into WAV files that we can actually listen to with some of our other audio utilities. Capturing an individual call. DECT CLI again, switch to the US bands, and then do call scan. Call scan will look for RFPI advertisements and note when there are new calls that happen by their identifiers. We haven't recorded anything yet. This is helpful when we run call scan and then there are no new calls, and you interact with an individual. Ben, can you take your phone off hook? Click, goes off hook, and then all of a sudden there's a new call. That's probably Ben. Hey Ben, off hook. Call goes away. Ben, take the phone off hook again. Click, call shows up. Same PP identifier. Hey, that's Ben. We can narrow it down to a call that we actually have permission to do so, if that's something that you need to be careful of. We now have a new call for an individual identifier, and then we can use PP scan to specifically record for that single portable part, as opposed to doing auto record that goes, oh, call scan, found a call, start recording. Whose is it? Don't know. Do I have permission to record it? I don't know. In this case, we can make some educated guesses about who we're actually recording, and again, back with some PCAP formatted output. We then use the DEC decoder shell script to do wave extraction using some audio command line utilities with SOCKS and our G72X audio decoders. Does all of the various varieties of the codecs because it doesn't know which one, and attempts to get both full duplex of the conversation as well as each one of them in half duplex as well, and creates a bunch of WAV files outbound, which we can then use standard Linux utilities to play back. So before you start this lab, shut down Kali, if you haven't done so already. I mentioned this on day one, and go into the settings and add a sound card. Because for whatever reason, the sound card got disconnected when we converted it to OVA. As part of lab, you're going to do some of this conversion from a PCAP and listen to some audio. If you play the audio back and there's no sound card, won't hear it so well. Some other things to think about on lab. Once you add the sound card to the virtual machine, you now have two independent audio controls, one in the virtual machine and one on your host. So start low and work your way up, because when you do the playback, it will actually decode some of the synchronization information for the audio, which is typically a waveform that has peaks and valleys. And it sounds like it's really loud, and then the audio comes through and it's kind of soft. So if you put some headphones on or you have your volume turned way up, you're going to hear, and then you hear some audio. So if you have headphones and you want to put them on, totally cool. But just be mindful that the initial parts of that transmission are going to be really loud. So taking a look at this with our packet capture and using DEC decoder, it extracts all of the raw data into .ima files from the PCAPs, and then attempts to convert all of them to various audio components. It's even telling us that we may want to remove the temporary files from the raw data extraction from the PCAPs. And by looking at the file names, we can start to see which codecs tended to work. Okay. Looking at some of these file sizes, 58, 44, and 44 bytes, not a lot of audio content there. And then looking at some of these other ones, the full duplex and the left and the right, the full duplex at 164K and the left and the right at 329. I typically have really good luck with the full duplex, even though the file is smaller. So that would be my recommendation for you guys as well. But it does all of them because we don't know which one, and it doesn't identify which one it's using. Some other attacks that we can do, we could potentially use the come-on air card to do fixed part, man-in-the-middle type of attacks or impersonation. Those cards were intended by Dashamond to be a fixed part, so you could pair your portable part with it and then use various voice over IP technologies so that you could communicate cheaper with folks overseas. That was their intent, so that you could roll your own voice over IP using DECT. Okay. It is possible for us to recover some user authentication keys, and the DECT standard cipher was considered weak. The Team Bedected folks were two university students that together looked at the security of DECT, which is where their tools came out of, for a master's project. One of the gentlemen went on to get his doctorate, I believe, in math. And he examined the DECT standard cipher and was able to break the DECT standard cipher as part of his research for his doctorate. However, it is largely an academic exercise in that it took only a couple of minutes to retrieve the key from a stream so that the data, when encrypted, could be decrypted. Only took a couple minutes with some GPU acceleration and probably would take less now. However, the sample size that he needed was a several hour-long conversation. So 2+ hours of source data for a 2-hour-long conversation to recover the key and the key for that session. Because every time you hang up the phone, new sets of keys. You could decode that 2-hour-long session, they hang up, they take the phone off hook again, new sets of keys. And if it wasn't 2 hours long, you'd never be able to recover those sets of keys. So largely an academic exercise there, but was noted that it could be done. The big thing we have here for doing some of these audits is the lack of hardware. The Dashamond cards are in very short supply, and that makes it hard for us to audit. So Larry, why do we care? If we can't audit it, that means no one else can listen to it either because they don't have gear because we have one set of tools. Laptops with PCMCIA cards, the Dashamond cards are becoming in short supply. Well, enter software-defined radio. There has been a resurgence in examining DECT with a radio that's software-defined. And in fact, There are at least 2 projects that will do some decoding of DECT. I've had this one working, which is pretty neat. In that you can use an inexpensive software-defined radio, the RTL SDR, unfortunately a different one than we chose for your kit. You have the RTL 2832U tuner chip, which unfortunately won't go to 1.9 gigahertz. However, the Elonix E4000 chipset will go to 1.9 gigahertz. The problem is that Elonix discontinued the E4000 chipset. And I don't want to have you guys have gear that, and tell you to get gear that is potentially end of life. However, a company called Newelec, when Elonix announced that they were end of lifing the chips, Newelec went and bought their entire stock of chips, something like 1.8 million E4000 tuners. And they put them in very inexpensive E4000 based RTL SDRs, and they have a little bit of a premium over the ones that you got. I want to say they're about $40 on Amazon. Okay. But eventually that 1.8 million will run out. However, we can use other software-defined radio platforms such as the Blade RF and the Hack RF, which are readily available, but they're significantly more expensive. With the Redected project, it will tune into the various frequencies, it will capture packets, and we set up some named pipes, and it will feed it to Wireshark. So we can get PCAPs. The problem is the PCAPs are a little bit differently formatted, and DECT decoder doesn't know how to deal with the output. So working on that. Yeah, it's one of my projects of 1,000 to try to get working. So I'd love some help if anybody ever wanted to investigate that. So we can, in fact, capture at least packets, and then we just need to find a way to extract them appropriately. Some other stuff is that there's another project, which is the one that I spent some of the morning and lunch trying to get to work, a project called GRDECT2. GRDECT2 uses the same RTL SDR E4000 chipset, the Blade RF and the Hack RF, and had some updates by Signals Everywhere. He does a whole bunch of software-defined radio stuff on YouTube. He's got a YouTube tutorial on setting up GRDECT. I was actually watching it earlier today. It does not output to PCAP, much like Redected does. It doesn't do any automatic scanning. You have to go and sort of futz around with it a little bit yourself. Okay. But Signals Everywhere is looking to update this in the future, and I think he probably has just as many projects as I do. Okay. But other folks are looking to update it as well. With this one, instead of writing data to a file or to a PCAP, it does real-time audio decoding. Fire up GRDECT2, find a call, it starts telling you that there's available data here, and then turn on your speakers. And it does real-time audio decoding for near real time as to what's being spoken into either the phone or the baby monitor. So we've got 2 tools, one for PCAPs and one for real-time audio coding, never the twain shall meet currently. So there are tools out there, and with the right tools for $40 that are reasonably available, or more expensive tools in the $350 range for the Hack RF, we can still continue to do some of this monitoring. All right. DECT, massively popular, starting to see a little bit of reduction in the consumer market just because many folks aren't using landlines anymore. We've got some dedected tools and some hardware for doing some examination. And we now also have seen the resurgence in investigation for DECT with the proliferation of inexpensive software-defined radios. I'm waiting for more of the software-defined radio to see some of these new attacks that were proposed by the Team Dedected folks, given that there's been renewed interest in some of this type of stuff. The suggestions for securing DECT are to migrate to a different system. Some of the systems were, they've got like, the DECT form has like DECT Pro now, which is completely different. But we're not seeing a lot of those come to market at all. And in fact, we've had some hard times even finding devices that are supporting it. The other one that they claimed used to be the next generation was a protocol called CAT-IQ. And the only CAT-IQ devices that I've ever found are an implementation of CAT-IQ in devices for law enforcement to be able to capture and decode CAT-IQ calls. Yet I can't find a device that actually makes CAT-IQ calls. So, okay. So, go hardwired, or in my recommendation, go Bluetooth Classic. All right, time for some lab in your workbook. Don't forget, before you start the lab, before you get going on all this stuff, add the sound card to your virtual machine. It does require that you shut the virtual machine off, add the sound card, and boot it back up. I hate to see guys, folks that get working on the lab, they're ready to play the audio and no sound card, so they have to reboot and then potentially go back and pick up where they left off. Do it first. And some of you may have already done it on day one. Good idea to verify that it's there before you really get working. It will make some noise. Please make some noise. Don't be embarrassed if it does. It's going to happen. Let us take a look at Zigbee. InGuardians does a lot of work with smart energy, specifically here in the US. So that's largely where a lot of my experience lies. I have done some other work, non-smart energy stuff, and Zigbee to me is kind of terrifying. The protocol is awful. If you go look at some of the code for folks that have tried to do Scapy for Zigbee and some Zigbee decoding, Scapy Com for interacting with Zigbee traffic and sniffing and so forth. The comments in the code are amazing. Because if you try to go decode a packet, it says, oh, you need to go here to decode this packet, this part of the packet. But you can't tell where it is until you decode this other part. But you can't decode that part until you have these other things. And it's like, how do I actually go and figure out how to decode some of these packets? And is awful to try to interact with. That said, there's some interesting failures with the way Zigbee is implemented for some security perspective. So let's take a look and sort of see what some of those are. All right, let's talk about why we have Zigbee. Talk about the technology through the layers and how the networks are constructed. We'll then talk about some of the security architecture, and then we'll look at some of the tools that we can use for interacting with and exploiting Zigbee, and a specific set of software tools with Killer Bee. We'll dive quickly into Z-Wave as well there. So Zigbee is a low-powered, short-distance, small packet size wireless protocol built on top of IEEE's 802.15.4. Small, lightweight protocol stack makes it great for implementing in small, low-power, embedded type devices, IoT, and so forth, where memory and footprint on disk is at a minimum. We have a bunch of different topologies so that we can extend those networks, which is incredibly valuable for stuff like IoT. So we can do star or mesh networking support. Some of the big design goals was to have it be small, easily implementable, easy to use stack from an API perspective, and have a long battery life. Using some very aggressive power saving techniques, the intent was to be able to put a Zigbee radio in a small sensor, say like a door open close sensor or window open close sensor, and have them do very aggressive power saving and run on a modest coin cell style battery for about 5 years. It's pretty good. Thinking about some of the other protocols that we've have in use, like Wi-Fi, the stack is pretty complex. It's fairly large, and the radios themselves require a decent amount of power, especially over long periods of time. Okay. And we see Zigbee making a lot of inroads into IoT. It's been a roller coaster ride for Zigbee adoption. We started to see Zigbee in the marketplace and would take off on what we used to refer to as embedded devices. And then it started to be a little lackluster and drop off when we saw some other emerging technologies. And then Zigbee took off when we had the Smart Energy initiative here in the US and others as well. Use of a lot of Zigbee for mesh networking in metropolitan areas for our power meters. And then after that happened and we made a big push there, we started to see a little bit of drop off, and now we have everything that has to be connected to the internet in some variety or be able to communicate to other stuff. So again, another rise in popularity with IoT. And now with IoT, I'm even starting to see other technologies in use as opposed to Zigbee because we have other radios that are popular in devices, and I see a lot more Bluetooth Low Energy. So we've gone up and down in the rise of its popularity from what I've seen in various environments in the industry, but still out there quite a bit in the IoT space. And you're saying, Larry, I don't have any IoT in my environment. That's what a number of our customers thought. And every once in a while we get to a customer in the middle of nowhere and they say, and we ask them, can we sniff for Zigbee? Even though we're not here to do a Zigbee assessment. They said, we don't have any Zigbee. Okay, so we'll sniff, and sure enough, they have some Zigbee stuff, and they didn't even realize that they did. They thought maybe it was using some other wireless technology in their environment, and or there are other systems maintained by third parties that have Zigbee in their environment, such as HVAC and so forth. So why do we need yet another wireless protocol? Lightweight stack, low power requirements, low cost, easy to implement from a stack perspective, complicated on the RF part. Okay. Thinking about some of the other competing technologies, Wi-Fi is complex and very resource intensive. Bluetooth is also resource intensive and has some pretty massive power requirements. Okay. Zigbee excels at being that lightweight sort of protocol that we can put in lots of small devices that only need limited types of communication for little bits of data as opposed to doing large-scale, high-speed data transfers. Why do we care about it? Well, in my opinion, Zigbee is connected to more things in our world that we can use to perform some type of kinetic action. Used on tons of smart meters in which we could potentially use those to turn on or off power meters to perform disconnects. As my good friend Don Wemmer says, the amazing ka-chunk when you actually pull the physical lever for the disconnect via something like Zigbee or via the optical port on a power meter. In stoplights, alarm systems, HVAC control systems for fans and waste gates and spill gates for water and water valves. If we can hack Zigbee, there's a pretty good possibility that we have some kinetic effect that we can have by manipulating those devices and the protocol. And this also becomes terrifying in that when they developed Zigbee, they didn't look at some of these other wireless technologies that had come before them, and they developed it in a vacuum and repeated many of the same mistakes other protocols have done and had to play catch up. And now they still also have issues. And we'll talk about some of those issues. Where do we see some of these? Smart thermostats, great for doing some power conservation and integrating with our various home control systems, potentially even integrating with our power meter so that we can have the power company adjust our power settings based on demand. I got really annoyed this summer. I happen to be using Wi-Fi for mine, but we could have potentially used Zigbee depending on the home control system. I have a Nest thermostat that is Zigbee enabled. And we opted in with our local power company to receive some reduced rates on our energy consumption as long as we allowed them to turn our air conditioning temperature up during the summer. And next thing I know, I'm sitting there in my office sweating. And I go out and look at the Nest thermostat and it's set to 85. and it's in like bypass mode by the power company. I'm like, no, and turn it back down to 72. It was one of those days that it was like 100 degrees in New England, which is kind of unheard of. So they did that a couple of times that week, and no, turn it back down, and I probably lost that energy rate. There's a bunch of different manufacturers of smart thermostats, Ecobee being one of them, that also uses Zigbee, and Nest also has Zigbee-enabled stuff as well. Great for power conservation and potentially some cost savings too. We can even take some of these older systems in potentially enterprise in some of our older buildings and adapt systems that were using relays and potentially dry contacts to enable them for Zigbee. Plug the wires in for the various fans and such that we need to trip connected to power, and now we can adapt those old systems to be able to use modern technology within our facility without having to replace all of these various systems within our building at huge expense. We can merely retrofit them. And I love some of these things for these Siemens field level network controllers for retrofitting some of these systems. Jay Hendricks, former Siemens manager for wireless solutions, has this quote saying, "Simply put, the network can't be compromised because the signal is automatically able to circumvent obstructions and find its target." I read this and say, Mr. Hendricks, please put down the crack pipe. Okay. How does a signal go around and make it so it can't be compromised? What I think he meant here was that, yeah, Zigbee goes around hackers, right? And will always complete its task. And it can't be compromised because it just goes around the hackers, right? Yeah, what I really think he meant is that it is not confidentiality or an integrity type of compromise. It is an availability compromise in that we can use Zigbee to build mesh networks with multiple paths. And should that availability be compromised, it can find an alternate path to circumvent obstructions. Still, it's quite funny to think that the network can't be compromised because it just goes around the hackers. I mean, that would be awesome. That would be an amazing protocol. Okay? And for the record, this quote is not why Mr. Hendricks is the former Siemens manager for wireless solutions. He actually moved on to bigger and better things and is actually a very intelligent individual. Some security systems, door locks. We can update codes via our home control system so that we can do like valet codes for the dishwasher repairman. So the dishwasher repairman can come into the house, fix our dishwasher and steal all our stuff while we're not at home. Give them temporary codes. We can have some recording and sending of when specific codes were used. Might be helpful when my 11-year-old gets off the bus and lets herself in the front door, that I can be away and get an SMS message from my home security system saying that your daughter just used the code to unlock the front door. And I can look at the cameras and see that she's got like 20 friends with her and a bottle of vodka. And this would be bad because she's 11. So the ability for us to have various interaction with different systems. Also might be helpful to tie that to our fire alarm system. So if the fire alarm goes off, it automatically unlocks all the doors. One, the kids can get out. They don't have to fiddle with the locks. And two, the fire department doesn't have to use their key. You know what the fire department's key is, right? It's called a fire axe. They just chop down your door. Yeah, they can just turn the knob now and let themselves in. The MGM City Center, Vidara, the Cosmopolitan, and what's the other hotel? The Aria. They have the world's largest Zigbee installation. They have tens of thousands of Zigbee controllers and end devices tied with NFC readers into in-room controllers so that you can control all aspects of your room and all sorts of fun stuff. And then you choose and it restores your settings and you can have your room just the way you want it. And like, That's luxury in a hotel in Vegas, right? Your room is always the way you want it because you've told it how you want it. For me, this is kind of neat. You can set the room up the way you want it, give it some schedules, and the part that is even better is, well, that's luxury for your trip. You leave and you come back a year later and you check in at the front desk. Mr. Pesci, thank you for coming and staying with us again. Your room is exactly how you left it. They retain those settings across multiple visits. So the next time you show up, if it's 6 o'clock, blinds open, lights down low, a little Barry White, a year later. That's cool and terrifying because they kept those settings. So lots of fun stuff. I've actually gone and done a little bit of Zigbee war walking a number of years ago, and I had a funny feeling that security knew that they were on to me. I knew that security was on to me because there was lots of security guards, big guys in suits, talking into earpieces, and while I'm walking by them saying, yeah, he's right there, type of thing. Yeah, there was a change your short moments where I thought some guy was jumping out of the bushes at me, wearing a suit, and I thought it was one of these security guards. No, turns out it was just some guy who was jaywalking across the strip and almost got hit by a car, so he was just diving off the strip into the bushes, and it just happened to be at me. Yeah, but nope, just I got lucky. Let's look at a little bit of Zigbee background. It was initially released in 2004. Open, no encryption, no message integrity check support. Similar to Wi-Fi, open, no message integrity check support, no encryption. They didn't learn from Wi-Fi's mistakes and quickly realized that they needed to perform some better security so we could avoid casual eavesdropping and manipulation. So in 2006, they started including some encryption, some message integrity support, and then shortly thereafter, with Zigbee 2007, Zigbee Pro, they enhanced some of the security models for being able to do centralized authentication and key distribution with a trust center, specifically under Zigbee Pro. Most Zigbee stuff works in the 2.4 gigahertz band, but different protocols, so not able to be inspected in our Wi-Fi radios. We also see some 900 megahertz and 850 megahertz, 900 here in the US, 850 in Europe. I was super happy when we built our new house and the power company came and put a new power meter on our house because I went and Googled for the FCC ID to see what type of radios were in my power meter, and sure enough, there's a Zigbee radio in it. I'm like, yes, I can attack my power meter. No, I can't because it's not mine. So I'm kind of glad I didn't and never got a chance to, because most of my gear is in the 2.4 gigahertz range, and this particular power meter has a 900 megahertz Zigbee radio in it. So my tool set doesn't match what's on my house, which is good because I kept myself out of trouble. All right, we use direct sequence spread spectrum for our modulation type, similar to some of our earlier 802.11 based technologies. And so 16 channels at 5 megahertz wide between 11 and 26, and a maximum frame size of 127 bytes. With the concept of a couple of different devices within a Zigbee network, the ZC, or the coordinator. It's the one that creates the initial network and assigns addresses when new devices joins and can provide some authentication. A router is a device that participates in the network, has some extra capabilities aside from transmitting and receiving data. It can also maintain link state so that it can provide routing over the mesh and be able to circumvent obstructions so that it can calculate alternate paths for packets. A Z, or a device, only participates, doesn't have the ability to perform routing. And then we have the concept of a trust center, the centralized source for doing a centralized authentication into the Zigbee network, and the ability to have a centralized key store. This ultimately gives us the concept of a full function device versus a reduced function device. I'd argue that one of the primary examples of a reduced function device is the Z, because it only participates, sends and receives data, and can't do any additional functions such as authentication like the trust center, key distribution like the trust center, or any routing like a router. couple of different topologies. Our star with the coordinator in the center and everybody reporting directly to the coordinator, whether they be devices or routers. And then the mesh network, thinking about the mesh network, what happens if one of these individual devices, let's say this router needs to talk to this device, yet there's some RF interference here. And this is the shortest path. RF interference here, Zigbee network can not be compromised and circumvent obstructions, so we can then maintain a different path through different routes. And I think that's really what Mr. Hendricks meant there. Looking at the packet construction, 127 byte maximum payload of 114 bytes doesn't give us a lot of areas for header information. We have similar types of things in our header like we would see with Wi-Fi. We have a couple of different frame types, beacon, data, command, and acknowledgement. We have the ability to have multi-length addressing within our headers. We can either do 2 or 8 byte addressing, and the number of bytes that we do for our addressing will determine the number of devices that we can include in any given Zigbee network. We can have 2 Zigbee networks on the same channel, just like Wi-Fi, and we separate those based on a PAN ID identified in those headers. That PAN ID is like the network name or the SSID under Wi-Fi. Just like we could have 2 Wi-Fi networks on the same channel, different SSIDs, and we know which packets to grab based on its unique identifier. The network layer is an interesting beast. We start thinking, physical layer at 2.4 gigahertz, physical layer at 2.4 gigahertz, the MAC layer at layer 2, describing our packets. The network layer, the NWK layer, doesn't really fit within one specific layer of the OSI model. It's typically between 3 and 4.5. It doesn't fit in all of those cases. It starts talking about address distribution for the Zigbee network itself, some of the security and profile definition, how we're actually going to be transmitting data. So when we join a Zigbee network, the first one on the network is the coordinator, and it sets itself as an address of all zeros. And then additional devices come to join that network based on that PAN ID, and the coordinator assigns addresses to those devices as they join. So, gives us the ability to record those addresses, where they're connected to, and the ability for us to determine route information. And our initial 802.15.4, so Zigbee security typically happens here as well. So here we have an example of a coordinator at 0000 and some traffic but to and from the coordinator itself. We do have the ability to do some encryption with Zigbee with the CCM star protocol. It is a lightweight variant of AES CCMP using 128-bit key length and the ability for us to have variable length message integrity checks. The longer the message integrity check gives us less room for actual data in some of our packets. AES CCM star requires that we have a key to be able to encrypt data that is the same on both devices. Now the question becomes, how do you get the keys on those devices? Looking at some of the security models for authentication to the Zigbee network. In the standard security model, any full function device can authenticate. Typically the coordinator is going to do that authentication. And then provide keys. In the high security model, the trust center, the centralized location for key distribution and authentication, is the one that will do so in later versions of Zigbee. So we need some keys to do encryption at the network layer. How do we get those keys there? Now, the first one is pre-installation, comes with a key from the factory for both link and network keys, so the master keys on the device. We could also do pre-installation from the factory, could update those by removing them from the box, grabbing a programmer and reflashing a set of keys to the devices requires us to touch every one of them. Got lots of devices, lots of consumers that may use these that may not necessarily have a programmer. Typically, we're going to see pre-installed keys from the factory. We want to have some dynamic keys because static keys on devices aren't particularly great. So we have two methods for distributing keys over the air. The first one, key transport method. New device joins the network. Hey, I have a key. Oh, that's great. We're going to send you a new one. You join our network. Here's a key in plain text. We send new keys to the devices when they join in plain text over the air. Great. Let's sniff it and capture keys, and then we can decrypt data. Not particularly good. The final one is SKKE, secure key negotiation. It requires that we have a pre-shared key on the devices, which will then create an encrypted tunnel, and then the keys will be transported over the air in that encrypted tunnel. The problem is that we need to have a pre-shared key on those devices to begin with, which means we either need to send that with key transport method in plain text over the air, or we use the default pre-installed keys, or we're taking them out of the box and touching every one of them. So SKKey is largely dependent on some of these other methods, which are not particularly good. We don't find a lot of folks, in my experience, doing SKKE because it becomes more complex. We see them either using the default keys or using key transport method, or relying on security protocols in some of the profiles at a higher layer. Thinking from a traditional networking model, something like HTTPS over a network that may be compromised. Using HTTPS over a WEP network or an IPsec VPN over a WEP network. So, similar types of analogy there. In the earlier Zigbee models for authentication, there was no mutual authentication of which networks we were joining and which devices were telling you to go away. So you could potentially craft some packets and tell devices to go away that weren't ever supposed to go away, or happily accept devices into your network when it wasn't the right network. They did have the ability to perform some validation, but not many actually did so. Within later versions, the Trust Center actually did provide some mutual authentication for those devices joining those networks. So network layer security, AES, CCM star, key assignment is difficult. We see lots of folks using default keys. But we can then start sending data and have our own each unique profile for securing that data as well, each using its own proprietary method per profile. There's home automation, building automation, healthcare, a whole bunch of different stuff, and each one has different revisions and different methods for doing their security. The one that I'm most familiar with is SEP, or the Secure Energy Profile. SEP1, or SEP, uses elliptic curve cryptography with intellectual property wholly owned by Certicom, which is a wholly owned subsidiary of RIM. Guys, the folks that made BlackBerry phones. Certicom has their intellectual property for elliptic curve cryptography for generating encrypted traffic for the smart energy profile. The problem is that there's one organization that holds the right to that elliptic curve cryptography. So if you need certificates for that elliptic curve cryptography, you have to go to Certicom. What happens when Certicom fails? Where do you get keys from? Well, RIM will probably sell Certicom, and then who will they sell it to? Okay, maybe some evil actor, or that someone that is potentially bad. Then the other questions is, when you have one group responsible for all of the key distribution and key management for some critical infrastructure, this becomes terrifying. What happens if they get hacked? And I will tell you that they have had some issues, because I may have been the one that found it. I was working on building some Zigbee devices to interact with some smart meters a number of years ago for InGuardians. And we were building some test devices, and we needed to obtain temporary certificates for our devices so that we could communicate with smart meters. So we didn't realize we needed 72 hours notice to get it done. So we sent the emails in, we made some phone calls to the one guy who could issue the temporary certificates. And as we're going through and filling out the form on the web page at Certicom that goes and does the CSR, the certificate signing requests and so forth on their website, we noticed at the bottom of the page we're getting ads for Viagra and Cialis. The web server that they use for submission of the data for the certificate signing requests had been compromised. Like, I'm giving crypto information on a compromised web server. So extra phone calls. Hey, you do realize that your web server has been compromised, unless you're trying to get us to buy, performance-enhancing drugs of some variety, ED drugs. Chances are that they weren't. They admitted as much. And then I think about that, and I'm like, well, if that web server is compromised and is using to generate the test certificates, how is that connected to the real certificates, and how far could they have potentially gone? The response we got back from Certicom was, if you think our test certificate generation stuff is in any way connected to the live certificate generation stuff, you're insane. I'm insane then, because I know how these things work. You probably didn't have it separated. So to me, that's terrifying. During this process, Zigbee Alliance said, hey, maybe we shouldn't be reliant on one set of folks for this particular profile. Let's go and, for electric curve cryptography that is, intellectual property by this one group, maybe we should go a little bit more open. And SEP 2.0, Secure Energy Profile 2.0, leverages open source and openly documented TLS to perform all of the authentication and then key derivation within the profile. We can use our own certificate authorities that we create ourselves using standard protocol. That's awesome. The problem is with the protocol, because they wanted it to be lightweight, they removed the ability for us to do certificate revocation lists. So what does that mean? You put a certificate on a device and you lose it, you can never revoke that certificate. How do we go attack some of this stuff? Well, arguably one of the best tools is the Killer Bee framework, initially written by Josh Wright and then turned over to a couple of folks at River Loop Security who have taken over active development. And in fact, I was actually submitting pull requests to them a couple weeks ago to fix some of the issues, simple stuff with the tools. And we got down to talking about some of the additional feature sets and potential hardware that it interacts with. Okay. Written in Python, interacts with a couple of different pieces of hardware for doing some sniffing, packet injection, decoding, and has a couple of utilities to perform some known attacks. So looking at some of the hardware, the first version is arguably one of my favorites, the Killer Bee hardware for the AVR RZ Raven USB stick. They run about $40 if you can find them. They were available from DigiKey and Mouser, searching for RZ USB. The problem is Atmel discontinued these about a year ago. You can still find some on eBay and so forth. And they do need to be flashed with an updated firmware with the Killer Bee project. If you are able to acquire these, and this goes for the folks on demand as well, if you get these and you want something, the Killer Bee firmware flashed on these, don't go buy the programmer. Drop me an email. I have the really expensive programmer. It takes about a half a second to reflash these. Don't spend the $80. Don't spend the $350. Have them drop shipped to me when you get them, or reship them to me for a couple bucks, and I'll happily program them and mail them back to you. There's been some new ways that allegedly on some of the newer devices that were coming out of Atmel, you could do them over USB. I haven't been able to successfully do it. So it's kind of a lousy deal that you have to spend a little bit of money, even with the AVR Dragon at like $80 by the time you spend the money for the board and the connectors. $10 for shipping to me might be significantly cheaper, and I get them turned around pretty quick. And the RZ-USB firmware with Killer B enables us to do additional packet injection and the ability for us to craft malformed packets, which may be very valuable. Another option is from the Riverloop security folks that are currently maintaining the Killer Bee project with their API Moat version 4. We don't need an external programmer for this. We can get it from Riverloop itself or from Atify store. They're a little bit more expensive than $40. They run about $150. They're fully assembled. They feature an external antenna connector, standard 2.4 gigahertz antenna. The RZ-USB sticks are built in on the board, so shorter range. Okay. We don't need any additional hardware programmers. It's updatable over USB. The hardware is all open sourced, as is the firmware on them as well. And there's firmware in them in the Killer Bee tree. The other one that I think that is actually pretty fascinating about this one is the API Moat version 4 is based on the MSP430 chipset, which is also in use for Travis Goodspeed's GoodFET. And we'll see in some of the other attacks that we can actually use a GoodFET to do key extraction for some PCAPs and such and memory for Zigbee networks. So this one now becomes a dual purpose tool. You can flash it to be Killer Bee and have it do packet captures, and then you can reflash it with the firmware for the GoodFET and use it to do memory extraction and other JTAG stuff as well. So you get two tools for the price of one, effectively, just by updating firmware. Pretty simple to install Killer Bee. We need to grab scapy.com from bitbucket.org and install that, and then clone the Killer Bee repository from Riverloop Security's GitHub page, and then run the Python setup. It gives us a bunch of tools for being able to do capture, replay, packet type modification, war driving, as it were, being able to locate devices, doing some attacks, and being able to locate devices for us to acquire, capture memory from, and then apply those memory captures as decryption keys to some various PCAPs. So lots of tools. Running through using some of these, we plug in our adapters, and in this case, using the RZ-USB sticks, the $40 version that have been end-of-lifed, and use Zigbee ID to determine which devices are available for us to interact with, and then using Zigbee Stumbler to transmit packets to say, hey, which Zigbee devices are there on all the various channels. And sure enough, we have a couple of devices that respond with various PAN IDs from our source of the coordinators, two coordinators for two different networks in this case, one on channel 15 and one on channel 11. Now that we know we have devices available and what channel they're on, we can use a Zigbee dump, which is a TCP dump-like clone, to capture data. We're going to tell it to use one of the devices, the 410 device, which is the RZ-USB stick version. Unmodified flash. We're going to capture on channel 11, so likely this particular PAN ID, and then write the output to a libpcap formatted file. If we use capital W, it will write it to Daintree DCF file format outputs, which are plain text, which we can then use the uber elite hacking tool VI, or VI improved, to modify packets. And we have tools to be able to convert back and forth between the Daintree and PCAP formats as well. Let's go capture packets and see if we can observe a new device connecting to a Zigbee network in which the key transport method, the over-the-air key transport, is in use. We observe that capture, and now let's go attempt to extract that from the packet capture. With the over-the-air transport method, those keys are sent in plain text, so it should be relatively easy for us to recover those. grab some packet captures, and then let's go and search through them with ZBD sniff. It recognizes the packet types for those over-the-air key transport method plain text packets, and then we'll pull them out and pull the keys from those packets for us. Okay. We'll only search one packet capture, but we can use some Unix command line kung fu to have it go through a bunch of them as well. And in this case, in the new client, the PCAP formatted packet, it found the distribution of a new network key in plain text. With Zigbee, there's a little bit of replay protection that is available, and they have a specific set of rules that when we encrypt data with Zigbee, we're not supposed to reuse IVs and keys, similar to like we had with WEP and WPA. Should never be reused. Must never be reused. The problem is we only have 16.8 million IVs available in a Zigbee network. And the Zigbee rules say that the specification says that if you exhaust your 16.8 million IVs and you haven't changed your key, you need to stop transmitting until you can get a new key on the device. But if you have stopped transmitting, you can't do over-the-air key transport method or SKKE, so you actually physically have to touch the device. And in a high utilization Zigbee network, you can send 16.8 million packets in a couple weeks or even shorter. So now every couple of weeks you have to go touch the device and reflash keys on it. So from a usability perspective, the protections to prevent replay are not very good. I mean, it's reasonable. Don't transmit using the same keys and the same IVs ever again. So we'll just shut down and you have to touch it. So what many of the protocol implementers across the various manufacturers have done is they've just chosen to ignore it. Oh, we ran out of 16.8 million IVs and we still have the same key. Don't worry about it. Just roll back to 1. Now we run into the problem of being able to do replay of packets just like we had with WEP, because we'll just replay with the same set of keys. And we can generate traffic for those same set of IVs because the way it tracks those IVs in use are in like a batch mode. Because they're small, lightweight devices that have flash that you don't want to keep writing to or you destroy the flash, it writes to the flash for that IV counter in batch mode, let's say every 10,000 or 100,000 packets in an increment. So we start with our IVs at 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. The IV counter is at 0. Let's say we're doing 10,000 increment, 10, 11, 12, 13, power it off. Power it back on. Stack comes back up, says, oh, IV counter was at 0. But I don't know whether I finished at 1 or 9,999. So I'm going to increment my counter to 10,000, and I'm going to start transmitting packets 10,001, 2, 3, 4, 5, 6, 7, power off. Power back on. Stack reads the counter. Oh, 10,000. I don't know whether I was at 10,001 or 19,999. Jump to 20,000. So what do? You make it transmit packets, and you just power on, power off, power on, power off, power on, off. So it increments that counter and then wraps back around, and then you can start sending packets back with IV of 1 again and do that pretty quickly. So now you can do inverse key deduction attacks by having different data with the same keys. So we can potentially run back to this whole WEP and ARP traffic acceleration, and then we can do brute force of those keys. So looking at this one, absolutely we can capture some packets. We can replay them with PCAPs, or we can replay the text as well. So, and then in this case, we're sending some replay of that new client with the key exchange that we saw earlier, and sending packets 10 times a second on the same channel. So in some cases, this replay-based attack might be interesting if they're not doing message integrity checks, in that if we capture the single command for like a damn spill gate to open 1 degree, and we capture it and replay it 89 more times, maybe we can force that damn spillway to open significantly further than was intended. So if we're not doing any checking. Some other stuff, lots of small distributed devices with keys in RAM and on flash. So let's find one, and let's go steal it. disassemble it, and then interact with the RAM and the flash chips to try to recover memory dumps. Okay. So in this case, we have keys stored on a device that are small and mobile. Once we have physical control of this device, just like WPA, WPA2 pre-shared key, we can potentially recover those keys from the device and then apply those keys to other sets of traffic for decryption. All right, so we can use some of the Killer Bee tools to go and locate some of the devices. It gives us some signal strength information on a speedometer so we can tell when we're getting close, and then go hunt those down and physically acquire them. We take them back to our underground layer, disassemble them, and then use something like Travis Goodspeed's GoodFET, or a reflashed API version 4, MSP 430 based JTAG interface tool, which through some of the tricks that Travis Goodspeed discovered gives us full access to RAM and flash by issuing erase commands, not actually erasing anything, which then unlocks the entire contents of the chip, in some cases where those keys are stored. Dumps all of that data to an Intel hex file, which we can convert with object copy. In this case, we're taking a look at a CC2530 development board, significantly larger than some of the real devices. Make it easy for us to start figuring out how we need to interact with that, to acquire RAM and flash over JTAG and dump that to file with the GoodFET. Once we have those files, we can convert those to binary files, take those binary files with Zigbee GoodFind, and then apply those binary files as decryption keys to a packet capture. So in this case, using our memory dump with Zigbee GoodFind to read from plain text capture, the Daintree DCF version, and applying the memory output to a decryption key. The problem is that we don't have any idea where that key is in that memory dump, but we know it's 127 bytes long. So we start at offset 0 and grab the next 127 bytes and apply that as a decryption key. 1, 28, apply that. 2, 129, 3, 130, 4, 131, 5, 132, 6, 133. Just take 127 bytes and offset by 1 and apply those as decryption keys to the packet capture. And eventually, we'll have gone through the entire memory capture and find a valid key. This one is kind of cheating because in this particular encrypted set of data, they use a default manufacturer set of decryption keys. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. We can put the packet captures into Wireshark and use these keys to decrypt the data and attempt to recover some of the commands available for us within that data. All right, Zigbee's hard. We don't do key revocation. Sending keys to the devices is difficult. Over-the-air SKKE with AES CCM star. There's some issues with IV reuse. There's all sorts of issues with the various source available, how we discovered that we could potentially do that IV reuse because they choose to ignore some of the specification. Zigbee's kind of tough from a security perspective, but we're going to continue to see more and more adoption as the IoT market grows. And as a result, I think we're going to continue to see more and more interest from attackers looking to be able to modify things kinetically with some of these attacks. And it is still very much some places that ongoing research continues. We haven't figured out everything with Zigbee because there's still a lot of attack surface left, and especially when we're finding that all of the different manufacturers choose to implement things poorly. Some other stuff has a similar set of tools, a tool suite as Killer B, is Z-Wave with the Killer Z suite. I'm seeing more and more Z-Wave in residential, home control, IoT, and so forth. And as a result, we start seeing these devices make it into enterprise, and even these technologies making it into various enterprise as well, as they start evolving into having more building and office automation. With Z-Wave, a little bit different frequency ranges, depending on where we are in the world, between 865 and 926 megahertz. We have some similar capabilities that we had with Zigbee, in that we can have network separation on the same frequency, identified by a unique home ID, similar to a PAN ID that we had with Zigbee, or an SSID with Wi-Fi. We do have the ability to do mesh networking and encryption with AES, but many of the devices choose not to implement AES to make them cheaper to implement. And we're really just starting to see the advent of folks delving into Z-Wave, largely because the intellectual property is owned by Sigma Designs. They released the specification relatively recently, open source, because they are now focusing on their Z-Wave Pro line, which they are retaining the intellectual property for under non-disclosure. So there are hundreds of thousands of millions of Z-Wave devices, and now the protocol is open. And now we can figure out how to interact with it. We can start interacting with that with the Killer Z suite. Killer B for Zigbee, Killer Z for Z-Wave. Makes it nice and confusing. Okay. So Killer Z suite gives us the ability to do capturing to PCAP, replay from PCAP. We can load those PCAPs into Wireshark. It does some limited analysis for us on the command line, and it's got a couple of attack and exploitation techniques. However, we do need some additional hardware for this one. And it is the RFCat dongle with the RFCat firmware based on the CC2540. Or if you wanted to not use the development version with the RFCat stuff, the Yardstick 1 from Michael Ossman is a great platform for doing so with external antenna connections. And definitely a proof of concept tool for Killer Z. There's some issues with when you hit Control-C and it doesn't stop, and if you don't have the device plugged in at the right time. But it's very effective in being able to demonstrate some of these attacks. Much like Zigbee, ZW dump is like a TCP dump clone, although it does actually give us some output on the command line. We need a couple of things. We need the country code for the appropriate channel and frequency, and we need the RF profile. Which RF profile is it? I have no idea which RF profile it's going to use. So I'll find a device. You set the country code, sets it to the right frequency for your country. In my case, it was the country code of US. And when I tried to do this capture, there are 3 RF profiles: Profile 1, Profile 2, and Profile 3. I started at Profile 3, just because why not? Hit Profile 3, sorry, not implemented yet. Oh, great, now I got a 50-50 shot. RF Profile 2, silence, hitting buttons on my Z-Wave stuff, nothing. So I stopped it and went to RF Profile 1 for US, and sure enough, I start seeing packets when I'm pressing buttons on my Z-Wave controller. And it tells us we're listening on our RFCat. We're getting some packets, identifies the home ID and the source and destination devices, and some of the types of packets and some hex output. And it's also writing it to PCAP for us as well. We can then replay those commands with ZW replay. In this case, I've been verbose with both of them in V. US profile, right channel, RF profile 1, where it was captured from, replay that the same, and replay from the original capture. It then starts replaying them into the air just as they were unmodified. So that's kind of interesting. they turn on the lights, I turn them all back off again because I captured that command maybe 3 or 4 days ago. Not a lot of time sensitivity here. So lots of opportunity for us to do additional stuff here, and the basis for us to have some framework here. All right. Lots of new devices with Zigbee, up and down on their market acceptance, and I think they're sort of back on the way up with more and more IoT stuff coming. We have some tools with Killer Bee, and now some readily available hardware, albeit a little bit more expensive. I've also seen some beginnings of implementation for interacting with Zigbee with software-defined radio, specifically the HAC RF in the 2.4 gigahertz range. Limited implementations, but they're getting there. Bastian Blosel started some of the projects. It was originally intended for Zigbee in the automotive industry, but it's expanded a little bit more than that now. Interesting for us to start looking at because it has some kinetic impact, and hence why I think many folks are looking to interact with that, especially where there's lots of smart energy items available that has some potential critical infrastructure impact. We poked a little bit at Z-Wave, also making additional inroads into the IoT market, and we now start to have a little bit of tools available as well. Time for you to work on lab.